Okay, they should be working now. So get your comments in. Hopefully people have found the right one. Unbelievable technical glitches with OBS, which is the streaming software. So yeah, okay, right. So let's go through the compilation process then for Aisha. So feel free to put your comments on the right hand side. I'll try and get through as many as I can. Obviously, I'll continue on for 2 hours. So I'm just going to start with program construction first and just quickly talk you through that. So looking at the screen there, there's 3 main things that we need to cover in chapter 1, or component 1, sorry, chapter 8, which is program construction. Compilers, interpreters, and assemblers are all forms of translators and stages of the compilation process. And then we've got translation and execution errors as well. So I'll write, as people comment, I'll write these down because people will just keep talking, etc. through that. So first one, compilation. Then we'll go through, we'll touch on big O. And then we've got insertion sort. Big O one. Okay, big O and okay, fine. Right, so let's have a look at program construction then. So program construction, really, you got to think of it as what sort of levels are you going to have. Don't forget, low and high level languages. We're sort of talking 4th generation languages now, which is your C and your Pascal and your C++. High level languages, that's what they are. The closer to English, the higher they are. You've got assembly language, which is written in operands and opcodes, which is something that people still do. And the reason why we do it is because you get tight control over the underlying hardware. So in things like your microwave and your kettle and your oven and things like that, they have been programmed in assembly language to respond very quickly. We've got machine code or machine language, zeros and ones, binary, dead simple. Well, not to write, but there you go. Hardware as well. Hardware, that is your transistors. So that is the thing, your switches that are going to react to your machine code. Okay. Looking at translation programs, we've got compilers, interpreters, and assemblers. They are all forms of translators. We use the term translators because we're converting code from one form to another, much like a translator would do if you were speaking German to English, etc. Your translator would convert your English into the German. And what we're doing here in the program itself, IDEs, they will have built-in compilers or interpreters, and their job is to basically convert your high-level language to your machine code. So let's start with compilers then. Converting high-level languages such as VB.NET, Java or C++ into machine code. And the point of a compiler is to think about one exe, so one executable file, and that means there is no need to compile over and over and over again. So in that aspect, it will save time. The program is compiled once, and that can be run many times, and you've got compiled code. It gets converted into machine code, so it protects the intellectual property of the developer. Unless you want to make it open source and allow people to view it, etc., then you can open it under an open source license. Okay, so compilers, start to finish, compile everything. Errors are produced right at the end, so usually it's not that accurate for errors, whereas interpreters, they handle it in a very different way. Interpreters are very much line by line, and the interpreter takes the first line of source code and translates it and executes it before moving on to the next. And that's good for errors because we know what line an error will occur on. Okay? Now, machine code produced while the interpreter is running is not saved. And that means that every time we want to run our program, we have to reinterpret that code itself. And that has its disadvantages in time. However, the benefit of that is that it can be ran on multiple platforms. Okay, so languages like basic Lisp, Python, JavaScript, things like that, they all run on interpreters. And like I'm using my Mac here, I can't use VB.NET on my Mac because it hasn't got an interpreter. It's a compiled programming language, so I have to have the IDE installed, and it's not fit for my architecture, so it won't work. So in order to be able to run it, you must have an interpreter installed on your system, much like Python is. Interpreted languages can run on any system as long as it's installed. And that's good because source code only has to be written once and it can be used across multiple software architectures, and that's good for money. So if I'm developing as a developer, then that's good for money. So you can easily inspect the contents of variables as the program is running. That makes testing much easier as well, because we can test single lines of code and see what the actual functionality of that code and what it's doing. Code can be run on many platforms, like we said. No problems with that. The problem with interpreters is that we need to have that interpreter installed. So that means a pre-installation of interpreter needs to happen first. And it can run slowly if it has to be interpreted every time, which is a bit painful. And developers can view the source code. And that means, your intellectual property is pretty much out of the window. So, looking at it, source code, compilers, hidden, interpreters, open source. You've got platforms, compilers, one specific platform, one instruction set, whereas interpreters, many different ones. For distribution, executable files are quite good because you can put them on a memory stick, a CD, transfer them over the internet or whatever. But I can do that for interpreter, for interpreted language, but I have to make sure that I've got something downloaded onto my architecture. So that's installing library or files onto my computer. Now, that's compilers, interpreters, but what about assemblers? Okay, so assemblers, their job is literally to convert assembly language into object or machine code. And this is what we used originally as developers were in the early stages of computer science. We were writing in machine code directly, and then we moved up to assemblers or assembly language because it was easier to do and there was less writing involved because programmers are really lazy. But it's a complex way of doing it. You need really specialist sort of knowledge to do that. Whereas if you think now with our visual languages and Scratch and things like that, it's dead easy to do. Children can do it. Whereas you give a child assembly language and they just melt into the floor. Okay, so the good thing is it's extremely fast. And that's the major benefit of it. And it can control directly transistors on the hardware, which is the point of using assemblers. So with assembly language, they'll have a direct mapping. So that's a one-to-one mapping. So if you remember one-to-one from our database topic, and that means we can write using mnemonics. And a mnemonic is something that basically has some sort of meaning. So when we use the add command, we know that means add. LDA is loading to the accumulator at the position of the register. So those things have meaning, and that's what a mnemonic is, and that's why we call it mnemonic. So each assembly code instruction has a one-to-one mapping with machine code, and that one-to-one mapping means there's no ambiguity. Ambiguity, all it means is that we have one decision to make it. It's going one way only, and it can't be interpreted as two different things. So if you think about it, as the assembly code has a one-to-one mapping, we've got a two-phase approach. So the first phase, the labels, which are the ADD, is converted into a memory address and stored in a symbol table. We've heard of symbol tables before, which is good. And the second phase of the assembly involves converting the mnemonics into their binary representations. Okay, so remember, take the label, convert it into a memory address, and secondly, that whatever's at the memory address, we give it a binary number, and that's a one-to-one binary. So that binary number is unique for that memory address. And the assemblers write machine code, it's not good. Okay, it's very time-consuming. It's prone to errors. These are things that are going to cost you as a developer time. Time is money in industry. So in order to do that, in order to convert source code, we need to use an assembler to get it into binary. Okay, and converting assembly code into machine code is known as assembling rather than compiling. So compilers and interpreters, compilers compile code, interpreters interpret code, and it gets compiled, and assemblers assemble code into machine code. So you might see this from my lessons. Source code can be split into translators and interpreters. interpreters translate it straight away into machine code. The compiler will convert machine code into, high-level languages into object code. And we also, any libraries that we use, any code that's written in the programming language that we make use of, then what we do is we link that together. Okay, goes through the linker, and that means the code is taken from the library and embedded into your object code, and then that gets converted into binary. But there is another stage involved. It's like a stage 2B. It can get converted into intermediate code after the linker. And what that is that allows an interpreter such as a virtual machine to interpret the intermediate code. It's sort of a partially compiled piece of code, and the interpreter can make use of that and convert it into binary. Okay, so virtual machines, we know what their job is basically. Their job is to act as sort of an intermediate onto your hardware. So I've got a Mac, and I can run Windows using software, and I can run Windows exe files in my Mac using a virtual machine. So intermediate code is partially or previously compiled. It's not fully compiled, because if it was, I couldn't run it. And source code is compiled into intermediate code to prevent the incompatibilities. Now, you've got to think, why isn't architecture not all standardized? It boils simply down to Apple want to make more money and Microsoft want to make more money. So yeah, we're always going to have that problem, unfortunately. Okay, so all of that process is all abstracted away from you. Remember, abstraction is taking things away and removing the complexity. The next thing we need to know in our exam is the compilation process: lexical analysis, syntax, semantic, machine code generation, and linking. So lexical analysis, the first stage of the compilation process, all white space and unneeded punctuation is removed. Okay, so in that process, the remaining code is turned into tokens. Tokenization, remember. Error messages are produced at this point if there is an error, and it turns our code into something like that you see on your screen there. Hopefully the quality is not too bad. I've not really checked, but hopefully you can see it. So every single part of it gets broken down. One second. And the point of that is that when we break things down like that, we create a symbol table in the syntax analysis part. So lexical analysis is all to do with the words and just tokenizing and breaking them up, removing white space and comments because it's not needed for the compilation process. It's just extra memory we don't need. So the syntax analysis, symbol table, dictionary, or a dictionary is created. Remember, the question will say reserve word and identifier tables, and we've seen those before. We'll have a quick look at one as well, just to jog your memory. Tokens are checked to see if they fit the grammar using Backus Naur form or regular expressions. Then we've got abstract syntax trees are generated. So that looks like our binary search trees, doesn't it? Then, if it doesn't fit the grammar, produce an error message. All right, syntax error has been produced. So this is a typical style of question that you might get asked about. It says construct a reserve word table and an identifier table that could be used to translate this segment of code into a stream of hex tokens. Okay, so reserve word tables, they look like that. So you have a reserve word that is defined by the programming language itself. You assign a unique hex token. You'll get marks for any unique hex tokens. And then your identifier table has an extra column. Remember, this is created by you. So the type has to be created by you. So it could have whatever data type you like. String, integer, real, whatever. So you just need to provide that third column in the identifier table. Okay? Now don't forget, if you've got brackets in there, each bracket, open bracket, is a separate reserve word and a closed bracket is a separate reserve word. I see a lot of students losing marks for that. So thinking about regular expressions then, you know, we did a little task in lesson on regular expressions. You won't get asked to build a regular expression, but the lexical analyzer, it searches through the code looking for specific patterns of letters and numbers, okay? And that specific rule that we use can be a regular expression. Some people used it in their coursework. You'll see some examples of them. But But we built up our regular expressions so that only specific things are allowed, and that's defined by your programming language. Okay. Now, regular expressions, we might need to know what they are. So they can be represented in diagrams called automata or state machines. Okay. Now, don't panic too much on this if you're not too sure what all these things are. Just remember, regular expressions are used to define the grammar of a programming language, much like Backus Naur form is. Okay, so if you have a look, it's a scary word, but we convert our regular expressions into an automata diagram. Okay, so the lexical analyzer can make the right choice of a token at any given point during parsing, which is the compilation process of splitting it up and etc. Okay, now this is an automata diagram. All right, just have a look at it for a second. This is a print command, and this is a lowercase az, and this is an uppercase az. So the variable can be made up of any character. It can be a lowercase character or it can be an uppercase character. Now, you won't get asked to draw automated diagrams, but you might need to know that they're used in the lexical process. So the print command here, the print command can only be one thing. It can be a P, an R, an I, an N, and a C, because that's defined by your programming language. And if it doesn't fit, then it won't work. So in Python, if you do a lowercase p or an uppercase p, then that's going to cause issues in your code, okay? Because the programming language is only allowed to be one thing or the other. So after the next step in the compilation process, semantic analysis checks that all the variables are declared and used. If we're not using them, then that's wasted memory, so we need to get rid of it. Are the variables declared in the right way? It checks that real values, for example, are not being assigned to integers or strings to integers, for example. It's checking rules again. So just think about the compilation process is making sure that we're writing the correct thing, because the computer can't understand the words that we're writing because it can't assign meaning to it. So it checks that the operation is legal. There's no mixed mode arithmetic. And we use reverse Polish notation, okay? So you won't be expected to know what that is. It is accepted on a mark scheme, but you're not expected to know that, okay? So once the string of tokens has been generated, the syntax analyzer, part of the compiler, checks whether the sequence of tokens is in acceptable order. So here, what about a variable? Variables equals constants. So a constant is some value. So think about that. A variable equals, could be a string, an integer. Is that allowed? If I write it the other way around, is my string, my constant, my integer, my whatever variable I've got, is that allowed to equal a variable? No. That's not allowed in the programming language. We can't assign things from the left-hand side over to the right. It must be from the right over to the left. So the first is acceptable and the second is not. Okay? Now, errors are still produced here. So if we don't stick to the rules, we get a syntax error. So syntax errors are when the tokens are passed to the compiler don't match the rules, and it can happen at any stage, really, the syntax analysis. Now, if the syntax is not 100% correct, then we can't construct a syntax tree, okay? And I keep banging on about these syntax trees, but they look like this, okay? So syntax tree is just each individual element of our code split down into a tree, much like we've seen in our binary search trees. We have nodes, parent nodes, and then we have children of it. And the way in which we traverse the tree will define our equation or our code. Now, each one of these, in the machine code generation section, the syntax tree has been created. So all we do is we assign the nodes of the syntax tree with its machine code, okay? And we'll allocate registers to minimize memory access. So the most frequently used are obviously going to get the main memory on, they're going to get the main parts of RAM, or they might use cache more frequently, etc. So this happens in the machine code generation part. Then we've got allocating registers to minimize memory access with optimization. So we optimize the machine code to improve our efficiency. So optimizing machine code is a real major step of the compilation process. Most programmers, they just write the code. It's quite inefficient what you write, actually, and you won't believe, even if I write code, I might optimize it, but it's not that efficient in the computer's mind. So the higher level the language, the more sloppy our code gets. Most programmers don't even care, or at this point now, in this modern day, we don't even care that the code is inefficient because we know the compiler will sort it out for us. Many compilers perform a number of optimizations for the developer, and one way to speed up a program is to limit the number of jumps it has to do. So if we can minimize that, then it's obviously going to speed our program up. Now, that's the compilation process in a nutshell. There's a couple of different errors that you need to be aware of. Execution errors, also called a runtime error, occur when the program is running. So runtime errors are errors which occur or which will cause the program or the computer to crash, even if there appears to be nothing wrong with the program. So running out of memory, for example, will often cause an error. So this can be because the instruction has been written in the wrong order and it's not making effective use of memory. You can also get things like dividing by zero, reading past the end of a file, or Stack Overflow of a data type. So an integer has a set range. If you go out that range, it's going to cause a runtime or execution error. And trying to access an out-of-range array element, especially during the searching and sorting, then that's going to cause an issue. Translation errors, syntax errors. So we discussed these before. Mistakes in the way in the code is written. And translators can only execute a program if it's 100% syntactically correct. Okay, spelling mistakes, keywords, they all get caught by your IDE before you actually compile, and that's to save time down the line. Your compiled code for whatever reason, and that causes a translation error. Okay. Now, let's see what the comments are saying. So I've got, what is it? So big O, insertion sort, we've got predictions for the exam. I'll have a look at sort of looking at what might come up on the exam later on. Yeah, Dijkstra seems to be something that's quite popular. Okay, big O. Okay, so Monso asking for what topics and questions might likely come up. Well, I can make a best guess, but it's not really something that's... The exam board was very unpredictable this year in the AS paper. So we'll have a look at some of the papers and see what questions have come up and what's not likely to have come up. I'll show you all the exam questions that I've mapped so far and what sections are quite weak, and then we'll focus on some of those. I'll go through... let's have a look. Compilation process. Right, let's go through the big O notation then, because that seems to be something that's quite popular. Okay. Right, let's have a look. So where are we? Big O's. So on that screen there, don't forget, some people have asked me questions about this. There are 9 chapters in component 1, and the exam board in the specification, I hope you've looked at it, the specification can only focus on these 9 chapters in the exam tomorrow morning. Okay, component 2, once you finish that exam, all those 9 topics, don't forget about them, but they're not your concern anymore. So let's look at big O notation. So that's in algorithms and programming. So there's a lot of stuff in here, really. All that stuff there, it's a massive chapter. Let's have a look at some big O notation. I'll skip through all the other bump and get to it. There we go. Right. Big O notation. It's a stickler, okay? People get very worked up and very panicked about big O notation. And really, I get why. It's quite complex, but let's try and clear it up. So, what is big O and why do we use it? Well, it was created in order to work out how your algorithm, the code you write, how it responds to changes in input of size. So when you add data in, how does the algorithm actually respond? Does it take longer to process? Will it slow down if you add a certain number of elements in it, for example? That is what we are checking, okay? The best algorithms are the algorithms that don't change in processing time, no matter how much data you add to it. So just think about it for a second. Think about a linear search. It's obvious. The more data I add in, the longer it will take to get to the end of the array. Obviously. So that's not going to be very good. Whereas something like a binary search, it removes approximately half of the data to start off with. So the more data I add, the more I'm going to chop off in the first pass. So that's going to be more efficient than a linear search. And big O notation assigns a big O, order of 1, order of n squared, or n log n, whatever. It will assign that to the algorithm to say, yep, this algorithm is pretty efficient. Okay? Now, the revision guide, I took this from the revision guide that you've got. So these are the things these are the main ones that we need to focus on. Okay? These are the likely ones that will come up in an exam, for example. All right? So order of n squared. So this means that the addition of an element has a disproportionate impact on the time or space required, possibly because the new element must be compared with all existing elements. So think about that. It's a bubble sort. It's an insertion sort. Think about a bubble sort. It takes the first element, compares it with the second one, and then makes a swap. And then it keeps doing that until the highest element is at the end. And then from there, we have to start a pass again, and we keep going. Okay? I'm just scrolling through the paper. Yeah, there's not an awful lot on that, is there? So each of the questions that have been asked so far actually cover programs with iteration in it. So that is really going to focus on order of n squared, okay, which is the one we're talking about. Now, the exam questions, if I head over to, I'll see if I can find this very quickly. It's in. Let me get it up for you. Got lots of documents open. So I'm just finding all the exam question document. Okay. Right, I've got it. We'll have a look at them in a second. So, order of n squared, disproportionate impact on time, usually very inefficient. Okay. Now, order of n log n, that additional elements increase the time and space requirements slightly more than in proportion to the number of elements. Now, this means that it's actually quite efficient, slightly more than in proportion to the number of elements. So the more elements I add in, the time will increase, but it won't have a major impact on that. So I can add in an awful lot of data information to my program, in my array, for example, but it won't have a major impact on that. So that's quite good. So quicksort, if you think about it, is it a better algorithm than the other sorts, than insertion sort and bubble sort? Yes, it is. Yeah. So order of n log n is actually more efficient than order of n squared. Order of n, the number of elements and the same time/space is needed to process them increase or decrease in proportion to one another. Double the number of elements, double the time and space required. So this is your standard graph with a straight line going diagonally, okay? And that's fine if it's a very short linear search. We know the best and worst case scenario for linear search is if I had a small amount of data items, then that's going to be fine. that's not going to have a major impact because it won't take an awful long time for my computer to search for each one. But if I add 6 billion items, then that is going to take some time. Additional elements, so this is order of log of n. So additional elements do not cause a great increase in time or space requirements. Consider negligible impact of adding an element to an array, which is then subject to a binary search. Okay? Now, if you to look at the graph of this, then what you would see, I wonder if it'll let me write on the screen. Of course it will. So in this one, you're going to have order of log of n. It's a very, you'll see it as a straight line right across the bottom, whereas your linear search is going to be sort of diagonal. The n log n is going to have a sort of a steady increase. It goes along like that and it starts to curve ever so slightly up. Then you've got n squared. It's pretty much like, well, not like that. More a sort of steady curve. It's quite efficient, and then it goes steep high up like that. So you've got to think about these algorithms. The best way to learn this is to sort of think about what algorithms go with which order. So log of n, quick sort, very efficient. Binary search, very efficient. So additional elements do not cause a great increase in time or space requirements. So how do you spot these in your exam? Well, you've got to look at what's actually happening. Will they get you to dry run something and get you to quote on the big O? Probably not. Will they give you an algorithm to try and get you to work out what big O notation? Yeah, that's more likely. That's what we've seen so far. Order of 1 is constant time. So where do you see this? Now, bubble sort and insertion sort. Yeah, it comes up here, but it says note that these examples refer to the additional space required. No matter how large an array is, a bubble sort will only need one extra memory location to facilitate the swapping of data items. Okay, this is also true of the insertion sort. What that's talking about is it's talking about when you take items out. For example, when you swap something in a bubble sort, you have to create a temporary variable. That variable is only ever one of them. That's your swap variable. To put the item in as you swap over and overwrite it, that's where it goes. Insertion sort, you have to take it out to create a gap in the array to overwrite it and then put it back in its right location. So that means that the variable is of order of 1. It's constant. That memory space is always the same for no matter how many elements you've got in your algorithm. That's the example that they gave here. Okay, adding elements has no impact whatsoever on the time or space required for the algorithm to run. This isn't on the graph, but if it were, it would have completely horizontal line along the bottom. So this is completely flat, which I'm not going to be able to draw because I'm left-handed. Oh, there we go. Look at that. Amazing. So, if I move this onto the screen, if it'll let me. Let's have a look at the big O questions that have come up so far. Okay, big O questions. So this here, let me just check. I've just realised I'm just neglecting the comments. I do apologise, but keep them coming in. I will get to them in just a second. So this was the sample one that's sent out. Now they haven't gone. They kind of followed this. They're starting to move off piste a little bit. So below is an algorithm that calculates the product of two square matrices, A and B. So basically multiplying A by B to get some sort of like an X and Y coordinate graph, rows and columns. So they got for I equals 1 to n, for j equals 1 to n, for k equals 1 to n. So that's three iterations to do something. The actual code is in this third iteration. Set answer ij to equal answer ij plus aik multiplied by bkj. Now, you don't really need an understanding of what's going on. It says determine how many multiplication calculations will be carried out when n is equal to 10. Okay? Now, what is going to happen with n is n is on the end here, but it's on the end of all three of them. So I will run 1 to n number of times. So let's say if it's running 10, it'll run 10 times, and this will run 10 times for every one of those, and this will run 10 times for every one of those. So that's 10 by 10 by 10. So that's 10 cubed, okay, which is 1,000. Now, this one, you just replace for 100. 100 times 100 times 100. That's 100 cubed. And there you go. It's 1 million. So that wasn't too bad. It was only worth 1 mark. But, you know, look at the words they use in square matrices, A and B. It's just confusing. Why would you use that kind of language? But they do. They will try and confuse you with the language. And that's what it's all about. They're trying to understand what you actually know. Okay? Now, looking at this, next one, you've got to evaluate the efficiency of the algorithm using big O notation. Determine the growth rate for time performance. Time performance. Okay? Look at the second question. Memory space. Space and time. Your answer should refer to the addition and multiplication calculations performed. Multiplication and addition. Okay? Now, it will specify in the question. If it doesn't, you're going to add all multiplication, addition, anything that affects the time of the algorithm, then that's what's going to be covered here. So have a look at what they've said. So the multiplication, the only multiplication occurs in the K loop. K loop, multiplication, where is it? There it is. There's the only multiplication that occurs. Okay? Since the loop will iterate a total of n cubed times, we know that because it's n by n by n. So that's going to happen 3 times inside the main loop. It'll execute exactly n cubed multiplication operations. So that's the multiplication. The addition, there are 2 addition operations. Okay? Where are they? It says one of them is here and incrementing of k. Okay? Now, incrementing k, you could argue, well, we increment j as well and we increment I as well. Yes, granted. Now, if you put that down, I would argue that that is correct. However, it won't have a major impact on the big O notation, and we'll see why in a minute. So each of these will happen n cubed times. Therefore, there are n cubed additions generated by the K loop. So 2 n cubed additions, because we've got 1, 2, going n cubed times. So that's generated by the K loop. The J loop has 1 addition operation incrementing j, which happens n squared times. So the J loop, they've counted that one. And also, they've counted the I one. So incrementation, it's because next n is actually, next k is k equals k plus 1. That's what that means. That is j equals j plus 1, and that is I equals I plus 1. Increment every time, because we have to count up to whatever n is. Okay? So this is the sample question. All right? So calculations might include assignment operations, but these will not affect the overall time. All right? So 1 mark for identifying the I loop is n number of times. Why? Because n is here in the main loop. So that's going to go n number of times. This is going to go n by n number of times because n multiplied by n. And this one is going to go n by n by n. So it's n cubed number of times. Okay? So n squared, n cubed for I, j, and k. Then you get 1 mark for the correct number of calculations. 2n cubed plus n squared plus n. Now, if I add data in to these and said, well, n is 10, this is going to go at a constant rate. It's always going to be 10. Nothing's going to happen. As I move this one and I add 10 in there, if I change to 100 or 1,000, then that is going to impact in time because it's going to grow by n squared. 10 times 10, 100 times 100, 1,000 times 1,000. But what's bigger is going to be n cubed, especially 2n cubed. Now, 2, really, that's a constant of 2. It's not going to make a major impact. So n cubed is going to be 10 times 10 times 10, which is bigger than 10 times 10 on its own, or 100 times 100, if this is going 100 times 100 times 100. Okay? So when it grows and you add data in, this is going to dominate. Okay? Remember, make sure you write that in your exam. This is going to dominate as n gets very big if n is given a number. So this is order of n cubed, this algorithm. Okay? So hopefully you can see that. The second question, using big O notation, determine the growth rate of memory space used by this algorithm. Memory space used. Now you've got to read the question for these. The algorithm will need to store 3 matrices, A, B, and answer. What the hell? It says in the question, determine the growth rate for memory space used. So what memory are we using? Well, what are we storing? We're setting the answer here. So we're getting this one. So this is matrices will require n by n items. But we're actually storing the variable here. What's it talking about? Well, look at the question. Both matrices have dimensions n by n, where n is the number of rows and columns in each matrix. So in the question, it specifies what it wants to do with the storage of this algorithm. Okay, n by n. So by doing that, algorithm will need to store 3 matrices, A, B, and answer. A and B, that's because it's A multiplied by B, and it's storing it in the answer. Each matrix will require n by n items. So when we store each matrix, it will be n by n. So the total storage will be 3, because that's the things we need to store. A, B, and answer. A, B, and the answer are getting stored inside the answer itself. And they're going to operate n by n, where n is the number of rows and columns in each matrix. Answer's a matrix, A's a matrix, B's a matrix. A and B, so n by n, I and J, n by n, I and K, n by n, K and J. Okay? It's quite difficult to spot that. So we've got 3 things being stored, A, B, and answer. N by n is the number of matrix, so it's 3n squared. As n increases, the storage requirements will increase. N squared as a constant is 3. 3 gets disregarded because as we increase, 3 will always be 3. Okay? So that means it's order of n squared. All right? In 2017, they asked this question. So I'm just trying to find, that's not a big old question. Let me leave that one for a second. Big old questions, big old questions. 2017, here we go. So they asked this question. Let me just quickly check the comments. Just get back to it. Shaq, yeah, that was a syntax diagram, yeah. Yes, it is live. Case tools. Shaq, they got 2n cubed because it was nested in 3 loops, inside 3 loops. I've seen modular programming, Dijkstra. Okay, right. So I'll do one more and then we'll get a move on. I don't even know what time it is. 1 o'clock, right? Okay, 5 past. So below is a part of an algorithm that sorts an array named X that contains n integers, where maximum integer is the largest integer that can be stored. Think about this for storage. We've just read a question that told us what storage requirements in the question itself. So, algorithm sort. Do we need to know what sort it is? No, we don't. We only care about what the algorithm's doing. We're not bothered. So, algorithm sort. Start equals 0 for I equals 1 to n minus 1. Smallest equals maximum integer for j equals start to n, blah, 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 blah. Evaluate the efficiency of the algorithm and using big O notation, determine the growth rate for time performance. 5 marks again, almost identical to the sample question in the way it was asked. Okay, so what are we actually going to do here? Well, you got to think about it. Time performance. Have we got any nested loops? I can see a for loop. I can also see a for loop inside of that. Where is the code actually being used? Well, for I equals 1 to n minus 1, it's going to set smallest to equal the maximum integer. Now that might not seem like it's doing anything, but that might make an effect on storage later on. We've got for j equals start to n. Okay. Now, it's going to go up from start to n. We don't know what n is, and that's the point of big O, because we're going to scale it up to whatever we need. So what we're going to do now is look inside that. If xj is less than smallest, then smallest equals xj, end if next j. So what's that doing? That's setting the smallest item, isn't it? Okay. Now, swap smallest with x start. Start equals start plus 1. Now, if you sat there looking at it going, well, what are we doing? It gives us nothing in the question regarding addition, multiplication, nothing like that at all. So, we need to just look at what the iterations are doing first. We'll get marks for working out what they're doing. So what's the I loop doing? The I loop is going to loop from 1 to n minus 1. So the I loop will iterate a total of n minus 1 times. What about the j loop? It's nested inside the I loop. So that means it's going to iterate j is going to go n squared minus 1. Why is it n squared? Because it's already inside a loop. There are 2 operations. Okay? 2 operations inside the I loop. What are they? So the first operation is the swap. So the swap, I'm just looking for it, inside the j loop. Yeah, the swap is inside our if statement. Okay? And the start equals start plus 1. Now that is inside the I loop. Don't forget this j stuff here, j, that thing in the middle is inside the j loop. That doesn't apply to the I loop unless we're talking about the j loop. So swap smallest with start. That will take some processing time. And start equals start plus 1. The addition operation means that we're going to have to do some processing on it. So that's going to be put inside the start. So it's got 2 things, 2 operations inside the I loop. The swap and the start. All right, so that's going to be 2 n minus 1 operations carried out inside the I loop. There's 1 operation inside the j loop. Okay, and that is our comparison. Okay, now we've got our assignment, but that assignment is memory. We're assigning it to memory. Okay, this is an operation. So any operation are things like addition, subtraction, multiplication, integer division, greater than, less than, equal to, that sort of stuff. Okay, so inside the j loop there's a comparison. So that because it's 1, it's actually 1n squared, but that just means n squared. So inside the j loop, n squared. Adding these together, we're going to get n squared plus 2n minus 1, because we had 2 things inside the I loop, didn't we? Okay. Now, looking at that, if we have n squared plus 2n minus 1, if we scale it up, what is going to dominate? Okay, so let me just show you. So in here, what I've ended up with is n squared. Oh, let's stop that. Right at angles. Okay, n squared. And that is going to be added to 2n minus 1. Okay, 2 operations inside the I loop. Inside the j loop was 1. Well, it was 1n squared, wasn't it? But that just gets disregarded because it's just n squared. What is going to dominate? If I add more data in, if I add 10 in, and 10 becomes n, and then that becomes 10, that's 10 times 10. That is bigger than this. If I do 100, 1,000, 1,000,000, doesn't matter what this is, that is always going to be more powerful. It's going to dominate. Okay? So, with that in mind, it's going to be order of n squared. Now, the top tip here is that anything with a power is usually more dominant. Okay? Usually. So, determine the growth rate for memory space used by the algorithm. Memory space used. So, the algorithm will need to store an array. One array. It's called X. It contains n number of integers. Okay? So, what is that? That's one array of n. So, it's one array, any number of integers. That's going to be 1 multiplied, one array, times by the number of integers. That's what we're going to store. Okay? As n increases, 10, 100, 1,000, it's 10 elements, 100 elements, 1,000 elements. So it doesn't matter what that's going to be. It's a constant, okay? So it's going to be order of 1, okay? So if we look down, we said this, we got order of n squared. Yeah, we got order of n squared. And then this one, the algorithm will need to store one array, n number of elements, n multiplied by n. N increases, the storage requirement will increase by n. Constant will be insignificant. So storage requirements will be order of n. Okay? So yeah, Shaq, you're completely right. Yeah, assigning it to a variable will be memory space. Operations, addition, swapping, anything that affects processing time is all about, yeah, I'm just reading. It's really hard to read and talk at the same time. Yeah, so that's anything that affects processing, okay, is going to be all about the first question. It's all about time performance. What effect will it have on time and processing? Okay? Whereas storage is memory storage. Okay? Right, so let's have a look at something else. I'll go back to this stuff here. So it's probably worth going through Dijkstra's algorithm. Okay? So, Dijkstra's algorithm. What's it all about? We have vertices, which is the plural of a vertex. A vertex is a single point. Okay? So, let me see if I can write on this again. In our graph that we see, this is a vertex, okay? The edge is a line segment that connects these two things together, okay? So an edge is a line segment, connects the vertices together. That's what that is, okay? So you got a vertex and an edge. Is that important? Not really. Just giving you some background. There is Dijkstra himself. So he created this graph, mathematical algorithm that basically works out the shortest path. Okay? This is technically a search algorithm. Why? Well, because we're searching for something else, some node somewhere. So the algorithm basically states, assign the initial cost of each node to infinity. Okay? Set the starting node to 0, add all the vertices to a set of unvisited nodes, and set the start node to be the current node. Okay? This will all make sense when I go through this in a second. Okay? For each unvisited neighbor, U, of the current node, or we call it C, add C to the cost of the connecting edge. So we're going to add C to our graph. If the new cost is less than U, replace that cost. So if we find a shorter route, replace it in the table. That's it. Remove the current node from the set of unvisited nodes, set the unvisited node with the smallest node from the unvisited set, and make that current node. Repeat steps 3 and 5 until we make the destination. What did I just say? That makes no sense at all. Okay? All that stuff is great. Okay? You won't be asked to define the algorithm. That's all garbage. Let's have a look at an example. I've made that table. You probably won't be given that table in your exam. You might be given a graph. Okay, there is an exam question which we will take a quick peek at. All right, that sort of made you draw the graph first. Okay, now we're trying to find the shortest path from, let's go from A to Z. So what do we do? Everything, the nodes in here, well, we've got to write all the nodes in. I hope I have enough. I hope I have enough boxes. A, B, C, probably don't. D, E, I've realised I've run out of boxes. F, what am I doing? My goodness. Let me get rid of those. I'm not even looking at the diagrams writing. Let's try again. So what node have I got? I've got an A. I've got a B. I've got a C. Yeah, good. D, yeah. E and Z. Okay. What is the current cost? I'm already at A. Okay, that's where I'm starting from. Okay, starting from A. B, no idea. Infinity, that you're supposed to set them all to infinity, but you get the point. They're all nothing at the minute. I don't know what the cost is, so it's really high. The reason why it's really high and set to in the algorithm is because as I go through it, whatever cost I find will obviously be less than infinity, and I will replace that. Okay? Now, I need to work out what's coming from A. So what can I get to from A? I can get to B. That's great, I can get to B for a cost of 4. Is 4 less than infinity? Yes, it is. Okay? So, where do I go? I go via A to get to B for a cost of 4. Can you see that? B, A, cost of 4. I go via A to get there. Okay? What else can A see? A can see C. A can see C. So C, get there for a cost of 2. And I go via A. Okay? Now, A can't see anything else at all. So the next step of my algorithm is to look at the table and say, what have we not visited yet? So we've not visited any of these. What is the lowest cost of all of these? Well, these are all infinity, which is a high number. And then I've got C, which is a cost of 2. So I go to my next lowest cost. So I go to C. So now I'm here. Okay? I'm at C now. What can C see? I can't go back to A because it's already been visited. I can see B, I can see D, I can see E. So I can see B. That will take me a cost of 1. But I have to take the cost to get to C first. That's 2. So it's 1 plus 2. So I can get to B for a cost of 3. My current cost to get to B is 4. So 3 is less than that. So I scribble out 4 and I put 3. Now, I don't go via A, I go via C. Then I check out the next one. D. I get there for a cost of 8 plus the 2 it took me to get to C. So that's a cost of 10. 10 is less than infinity, and I go via C. E is a cost of 10 plus the 2 it took me to get to C. So E is going to take me 12, and I go via C. Okay, I can't see anything else. So C's done in my list. I've done A, I've done C. What do I do next? The next thing is look at the smallest cost in my table. So I'm just reading the comments again. Yeah, tree traversals. Yeah, they're comp one. Yeah. For that big old question about time space, is there a way to skip to the answer if you are told the dimensions of n? Yeah, you can jump straight to the answer. You will get a mark for the answer straight away. If you can see 3 loops and it asks you the time complexity, it will be order of n cubed, for example. You can see it straight away, yeah. But you'll only get 1 mark for that. You have to show the process of getting to it for 5 marks, George. Okay. Yeah, Tanvir, I've seen that. Modern div is quite straightforward, Tanvir. Yeah. Modular returns the remainder. So when you divide something by 2, for example, if you mod something with 2, if it returns a remainder of something, you know it's an even number. Okay, if you mod something with 2 and it returns 0, i.e. no remainders, then you know it's perfectly divisible by 2. Div is just your standard division, it's integer division. So that returns the whole number. And BNF syntax diagrams, okay, I'll write that down. So, where was I? So I have been to C now, check that off. I go to my next lowest number, which is B. Okay, B's got a cost of 3. What can B see? B can't go to C because it's already been checked off. B goes to D for a cost of 5. But I need to take the 3 I've already got. So take 8 in total. So to get to D, it's going to cost me 8, which is actually more efficient than this. So I put 8 in there and I go via B. Okay. Now B has seen D, but it can't see anything else. So that means B is completed. I look in my table now, just to check these off. I've been through A, I've been through B, I've checked C, I've been there. Where have I not been? What's my lowest cost? 8, 12 or infinity. 8 is my lowest cost. So now I go to D. D can't go back to B or C because they're already seen. And I check out E. E's got a cost of 3. Okay, to get to E, it'll cost me 3. Plus my 8 that I've got in my table. So that's going to cost me 11. Okay, don't know why I'm rubbing it out. Okay, that's 8. It's going to cost me 11. So that is less than 12, 11. And I go via D this time. What else can it see? Oh, I can see Z. So D checks Z out. Says, well, I can get to you for a cost of 6. What is my current cost in D? It's 8 before I'd started scribbling it out. So that's a cost of 14. So 14 to get to Z via D. Can't see anything else. D gets checked off. I go to E because it's my next lowest cost. What can E see? E can get to Z for a cost of 2 plus the cost of whatever E is. That is 13. 11 plus the 2 is 13. That's less than my current cost. So 13 gets put in there. And I go via, not C, I go via E. So that means that E's been checked off. And this is my destination node. So how on earth do I work out that my total cost, I know it's 13. That's how much it's going to cost me to get from there. So how do I get from, what route did I take to get from A to Z? Well, I look at it and I put Z first. Then I went via E. Then I look at my E in my table. That went via D. D went via B. And B went via C. C went via A. So it's A, C, B, D, E, Z for a total cost of 13. Okay, that's Dijkstra's algorithm. All right. So we did have a Dijkstra's algorithm question. It was a different style. Let's see if I can find it. So it's still in here. Here we go. So this was the Dijkstra's algorithm question that was asked. Explain what is meant by a shortest path algorithm. So it will analyze a weighted network to identify the shortest route between two given vertices or nodes. That is confusing speak for to get from one node to another, it calculates the shortest possible route and which nodes to take. Simple as that. So the routing costs for a network of 8 nodes are stored in a 2-dimensional array. So this is a 2-dimensional array. You've got your X and Y axis as shown below. 0 indicates that there is no route between the nodes. So between A and A, there's no route, there's no node. Obviously, look at this diagonal here. There's no route because it's like A to A, B to B, C to C, D to D, etc., etc. Okay? So here, draw a labeled diagram of the network. Interesting. So from A, if you look at this, most people, when we did this in class, most people pick this up sort of intuitively. A to B will cost you 5. A to C will have a cost of 3. So A only connects to B and C by the looks of it. B connects to A for a cost of 5, D to a cost of 7, E to a cost of 2, etc., etc. And you go through and you build it up. So this is what you will end up with in total. Okay? That's what you're going to get. So once you've done that, and you've built that, the next step of the question is to state the shortest path. Now, look at the marks for that question. State the shortest path for node A to G and calculate its cost. Okay? Now, calculate its cost for 2 marks. You're going to get 1 mark for the sequence and 1 mark for the total. Okay? Now, my advice to you, if you see the question and it's worth 2 marks, your human brain can look at it and just calculate it and get to the right answer. You can look at it, you can trial out all the different methods. You don't even have to do the algorithm I've just shown. The algorithm I've just shown you will get you more marks, probably 5, 6, maybe 7 marks. In this question worth 2, you tell me the total and you tell me the path and you get 2 marks for it. The table gets you no marks. Okay? So that's Dijkstra's algorithm. So you follow it, everything's given infinity, you check each of the paths, and then all you do is you calculate the lowest cost at each node, see what's the next available path. If it's less than that in your table, replace it, and you get to your end node. Okay? And that's it. Okay. So what I'm going to do is I'm just going to have a quick break just to get a drink of water, and then we'll be back. So I'll check the comments and see what the next topic is. Okay, so just in response to some of the comments, Callum, no, it doesn't matter if the lines are all over the place. You can draw them curved. It really doesn't matter at all. They're not bothered about that. As long as you've got the correct weightings on the edges, it's fine. What else? What's those two? We'll go through some. I'll finish off with the sorts and searches, I think. If you are looking for questions, if you want to see me go through the exam questions on Big O notation, there are videos on that on my channel. You can refresh that and go through it. Okay. Right, so right, okay. Right, let's have a look at let's do modular programming. Modular programming. So it's not as scary as everyone's making out. Maybe it just needs a bit more information on it. Let me find modular programming. There's a lot of stuff in chapter 3. That's why. So search and searches are there. Comparing algorithms. Okay, big awesome. Okay. Yeah. Okay. Right. I'll just leave that up there for a second. Just want to make sure that everybody covers sequence selection and iteration. It's called repetition here, but it is called iteration as well. So if you see repetition in your exam, don't panic. It's actually called iteration. We've got counts and rogue values as well. Rogue values is not something we typically talk about, and this is an invalid value. Okay, so it's used to indicate a special case. So consider the word hello, with each letter having an index. H is 0, E is 1, etc., etc. The index of X is -1. Okay, so if you go through the alphabet from H, etc., you'll get to -1. And since the index cannot be below 0, this is a rogue value. So what it means is X isn't present in that word, so it's not taken. Rogue values are really strange, and you don't usually see them in programming. You usually get an error relating to it, but all it is basically an invalid value that is given, but it cannot be used in the programming language. Okay. Count variables are to keep track. So things like our loops, it's inside our iteration. The next is a count. Basically, it keeps track. For I equals 1, I is a count variable, and it's local. Those variables are local, and they get destroyed within the procedure. Sequence, line by line, follows it in the order it's written. Selection is our if statements, and we've got repetition. So we've got for loops, while loops, do loops, etc. So modular programming then. Okay, now modular programming. Oh, Tanvi is asking me mod questions. Someone can answer you in there, Tanvi. Someone that knows it. Okay, so modular programming. What is a module first? It's a self-contained unit of code. So its job is it's like a procedure or a function. That is a module of code, and its job is to just action things or return if it's a function. Okay, so remember, procedures are code that runs and it will do a job. Whereas a function will do something, it can get past parameters, as can a procedure, and it will do something with them, and then it will return the value later on. Okay, what is the point of using procedures and functions? It's more efficient. It reduces repetition of code. It allows you to partition and modularize your code up into sections. So someone can work on a procedure or a function to do something, and it can be used many times by lots of people. Okay, so modular programming, what's the benefit of it? So separate modules can be allocated to different programmers. So when you break things up and you decompose and you modularize things, the process can be broken down and it becomes more manageable and more simple. So think about your coursework. You built your coursework. If you were to do all that in one go, it's quite a big thing to do. What you want to do is you want to break it up into smaller chunks and tackle something like, oh, I need a function to return the customer's position. I'm going to use that loads of times, so I'll put it in a module. I'll make it public, for example. So that the first thing is separating the modules down into smaller, more simple tasks. Okay? And the benefit of doing this, in industry, you would have programmers with different specialisms, and they can be assigned to different modules that match their skills. So if you've got someone that's really good at programming searches and sorts, then you would give them the procedure to do that. You would go, right, you program that procedure and you go and do it. And then they will come back with the procedure all programmed with the sort, etc. And you'd move on. So you can suit different modules to suit different programmers with different skills. modules can be designed separately away from the system and tested separately outside the main scope of your program. Now, why is that beneficial? Because it doesn't have to be tested, mixed in, combined with the program, which might change its functionality, the way it works, etc. This can be stood on its own, designed, tested, and produced, and that's it. The good thing is you can produce a full test report, you can do alpha, beta testing, you can do white box, black box testing, all separate on your procedure, on your module, before you introduce it into the system to check that it works before adding it into your main system. Okay? So, any module that goes through this process is obviously going to have less bugs, okay? Now, the good thing is, you can make it fully watertight, bug resistant before you add it into your system. And that gives you a certain amount of protection. So people can't come back to you after and say, well, it was your procedure, it was working before your procedure was added or whatever, or we're getting strange errors due from your procedure or your function. You can say, well, there's the testing, there's everything we did, nothing wrong with it at all. Now, like I said before, the reusability of code, really, I would argue that is the main benefit. So a module can be reused, okay? Code doesn't have to be copy and pasted. A lot of you did modular programming without even realizing it. A lot of you didn't do it. A lot of you just stuck all your code and copied and pasted it and changed the variable names, etc., which is not modular programming. Modular programming is splitting up a big task into smaller tasks, programming that, and then combining it all together. Okay? So it reduces the volume code and often the number of bugs and the amount of testing and all that stuff, and there's lots of benefits that come with that. So there's three different things. You need to be aware of then for modular programming. Let me see if I can work this then, or remember how to work it. So these three things in modular programming are, the first one, something called a standard function. And honestly, you've used all of these before. I can promise you've used them before. All right, a standard function. So what is a standard function? So pre-written, this is a subroutine, procedure, or a function that performs a commonly required task. So what did I see people do in their coursework? Like I said before, find the ID of a customer. Okay? You might have used a standard function to, I don't know, add the number of people in a list. These are all things that are made just to make your life easier. Why would you recreate all the code over and over again? It's just not relevant at all. So, the next one you need to look at, you probably use one of these as well, without realizing, something called a standard module. Yeah, Fahim, you can go back and have a look. Yeah, standard module. So a group of related standard functions, okay? So we've just talked about standard functions, but these are related, a group of them, related standard functions. So our standard functions, they will contain, in standard modules, it will contain all of the variables of your standard function. It'll contain all the information needed to run them. So it will combine and if I draw a diagram, might explain it a bit better. This, without touching on classes and stuff like that, I will go through paradigms, but this is, think of it like, this is a standard function. I'll put standard function. Okay? It'll combine the result of this standard function, and it will use the result of this standard function. Standard function. So if you did a module, you didn't really use it like this, but this is your module, and you've got multiple standard functions that are grouped together to produce a final result. Now, you may have not done this. You may have just used the module for straightforward information gathering. You might have used it for just being called somewhere else in the program, for example. So you didn't really use standard modules like they were supposed to be used. Really, what they do is they bring everything together in one area to be used for related tasks. So like if you're doing something for your customers, you might have get the name, get their address, get the postcode in 3 different standard functions, and this combines all that process together for you. Okay? So really, the last one that you need to know is something called a user-defined subprogram. So these, you may just call these into the standard module, but user-defined are really, they're written solely for or by the user. And they don't always get used. They might be used once or twice. These are frequently, these are not as frequently used as standard functions or standard modules. Okay? And this is where you write your own, usually they're local, so you write them in your own class and you would call them as and when you need them. So they're not really planned. Let me point out that these may come as a part of the programming language. Now, you've definitely used these. If you've done GCSE Computer Science, you've probably used these as well. You might have done in your coursework. So, like I always go on about, like .toString, for example. Yeah? You didn't write that. Message box? You didn't write that either. Okay? So, these are hidden, usually in libraries. So, they're all a part of your standard functions. Think about user-defined subprograms as something that you would write, okay? So you do them. I'll put locally. You do them locally. And this is all about reducing repetition. It's all about reducing repetition in user-defined subprograms. Okay? Now, it's up to you what you do with those. You can declare them locally or globally. And go from there. You can use them in classes. You can share them across. You can even move user-defined subprograms into standard modules, and you can use them wherever. So in modular programming, remember, modules can be split down, or problems can be split down into smaller subproblems, or decomposed. They can be given to different people, different programmers. These programmers can have different skills. What's the point in doing it? To reduce repetition of code. It'll have fewer bugs and errors because it can be tested as a standalone. You've got standard functions, standard modules, and user-defined subprograms. The subprograms are done more locally. They reduce repetition. Standard modules bring standard functions together for a common goal and keeping it all packaged in one place. Standard functions are a part of the programming language, can be written. You can actually write them as a part of the programming language, but you don't work for a company that does that. So they also help with the functionality of your program. Okay, and that's standard modules in a nutshell. So let's have a look what is next. So is do while not end of file classed as standard function? Yes, it is. Yeah, Tanvir, yeah, that is classed as that. Anything you've used for files, like file open, file close, etc. You have not written any of that code. There's a lot more code that goes on behind the scenes, but you've not looked at that. Okay. Hi Mark, algorithm question. I can go through some algorithm questions. I've written that down. Okay. If you were doing a reserved word table, would statements like if, while, for, next count as a reserved word? It's embedded in the program language. Like, yes, it is. Yeah. So they are all a part of the reserved word table. So yeah, don't forget the end fors and the nexts and things like that. That's all a part of it. Else and end if is all a part of the reserved word table. What else have we got? Okay, case tools. So please do keep suggestions coming in. I'm just going to the top of the list. I've done compilation process now. Big O was done. Like I said, go back and have a look at some videos on that where I can spend a bit longer talking through that. The sorts and searches. Well, yeah, let's go through the sorts and searches then. And then I'll do an algorithm question. So that's in algorithms and programming again. And we've got sorts and searches. So with the sorts and searches, there is an awful lot of stuff out there. Videos, etc. to help explain it. Animations are quite good. So in order to save that time, I won't go through how to move it around in an array graphically, etc. I'll talk through the pseudocode. This is inside the Google Drive folder that I've given you all. This is inside there. All right. So I think it's best if I talk through what the pseudocode looks like and what the exam pseudocode produced. Okay, so it's probably best if I go through the exam pseudocode. There's textbook pseudocode there, but it's not all there, if you know what I mean. It's sort of more Python based, whereas the exam board might as well go from that because that's what they've given us. Okay, so here we'll start with our sorts. There's 3 sorts that you need to know, obviously. So we've got our bubble sort, insertion, and our quick sort. So bubble sorts, make sure you start your procedure sort my array. Okay, start procedure will usually get you a mark. We've got, let's get a pen. We've got n is integer, temp is integer. Remember, because when we do a swap, we have to put the temp in a box. So temp swapped is Boolean. Set n equals length of my array. Now it says that this is how they do their comments in an exam. So return the length of my array. Repeat. So this is a loop. Okay. Now, remember, a bubble sort has 2 loops. It has 1 loop for swapping and 1 loop for passing. Okay, so this down here, this is what we call our swap. And this is our pass loop. All right. So yeah, so we've got the length of the array. Why do we need that? Because we're going to go until the end of the array. Now, if we reach the end of the array and nothing is swapped, then we know that we're gonna finish. So repeat until swapped equals false. So until we finish swapping, until we do no swaps, on a pass, we're not going to finish. Okay. So if a pass is made on a pass, then we need to continue doing a pass. So we set swapped equals false to start off with, because we've not made a swap on this pass. So the first pass we go through, we've not made a swap yet. For I equals 0 to n minus 1. Okay, why do we do n minus 1? It's because when you go through a full list, you don't check. If you've got an array of one element, you're not going to check that that's greater than anything else, are you? Because that is it. That's why we do n minus 1. Okay, so for I equals 0 to n minus 1, if the array at position I, remember how arrays work. Draw out my arrays a bit better. Okay, you start off at 0, 1, 2, 3, 4, 5, for example, up to whatever. You index them, their elements are indexed by their array index. So starting at 0, 1, 2, 3, 4, 5. If my array, this is the identifier, my array, it's the name of it, my array. Come on, play ball, graphics tablet. If my array at position 0, I, because it's 0, I, is less than my array plus 1, so if that is less than that, then what do we do? Well, here, because this is going, if you think about this, why is this less than and why would it be greater than? Okay, so if it's less than it and we're making a swap, then that means that the lowest number is going to be at this end. Okay, if that was greater than, then what we're going to do is we're going to have an ascending list. Okay, so watch out, because that usually is a question. Okay, that usually is a question that try and catch you out on. All right, so if my array is less than my array plus 1, the one next to it, so if that one here at 0 is less than this one here, then we make a swap. What does our swap actually do? Now, temp, that is our variable. We was talking about it before with our constant stuff. Temp, my array plus 1, so whatever's in there, let's say it's 5, okay, that has to be put in a temp variable. Why does it have to be put in there? Because we're going to overwrite it. 3 then gets replaced with 5 because array at position I plus 1 is given the value of my array I. So my array I is this one. Is passed into this one, so 3 gets overwritten, and now 5 has disappeared. If we didn't put it in a temporary variable, yeah, then it would be lost forever. Okay? I really do want to reference Sandra Bullock in the film again, but no, I won't. So my array at position of I is given the value of temp. So this one here is given the value of 5 because it was stored in a temporary variable. And swapped equals true. Why is swapped equals true? Because we made a swap, people. We made the swap. So there we go. So then if that's true, we're not going to end... we're going to continue, all right? Because it's not false. It's set to true now. So we're going to continue doing this until we get to the end and it's false. So even if we swap one thing and don't swap anything else, tough. We have to do the whole pass again, which makes it quite inefficient. Then we end the procedure, okay? Top tip with pseudocode, always make sure you end your fors, end your ifs, and end your procedures, okay? So that's the bubble sort. Now, the insertion sort, a little bit different, obviously. So with that, with my pen again. So again, we declare our procedure. An array is given, 0 to 3 is integer, so it declares the array. I is integer, j is integer, n is integer. The current item is integer, inserted is Boolean. So 0, 1, 2, 3. Inserted is Boolean. Set n equals the upper bound of the array. So this is the total number of items in the array. 1, 2, 3, 4. Okay, so that's going to go to the upper bound. For I equals 1 to n minus 1. So that means, because it's starting from I equals 1, hopefully you can see that, we don't actually make use of this box at all. So that element there, that element box, we don't even use it. We start from 1, which is another thing you've got to be mindful of in your exam. Where are they starting from in the array? So for I equals 1 to n minus 1. So whatever that is, it's going to go from here to here. With my very strange bent arrows. Okay, so we're going to do this until we reach the end of the array. Set the current item equals, so current item, that variable is going to be given the value of my array at position I. So whatever value this is going to be put inside there. Okay. Set inserted equals false because we've not inserted anything. Set j equals I minus 1. So what's j? What is j? Well, we know what I is, so we can work out j. So I is 1. I is 1. Minus 1 is 0. So j is actually 0. Okay, so that's set to 0, which might seem strange. But what we're going to do, this code, do the code while j is greater than or equal to 0 and inserted equals false. Now I remember this algorithm from a dry run. You run this through about 3 or 4 times and nothing happens for the first sort of 3 passes. Okay, so it'll take forever to get through, but I'll explain the code anyway. All right. So while j is greater than or equal to 0, now you've just set j to 0 and inserted equals false. And you've just set that to false as well. Okay? So, but we're going to do this. We always do one pass first before meeting the condition. All right? So we'll do this code and inserted will either get changed to true or false. If nothing happens and j is 0 and inserted is false, so that needs to be 1 and that needs to be 1 or true and true in order for the whole thing to pass because of that logical operator. Okay. Now what the insertion sort does is it will go through and check to see if this is bigger than this, and if it is, then it's going to make a swap. So this is going to make a swap with this one, and it's going to move down the list. Now the point with the insertion sort is that it sorts as it goes. And that makes it more efficient than a bubble sort. Okay. So if I had some numbers in here, 2 and 1 and 5, for example, how would this work? It would check that 2 and 1. Is that less than that one? Yes, it is. So we need to actually move it. Now we need to create space in it, which means we're going to have to use a temporary variable to put it in there in order to make the swap happen. So 2 would disappear, 1 gets put in, and then we put 2 back into this position, but only if it is the first element. If it was longer than this and 5 was further up, for example, we'll check if it's less than 5. If it is, swap with 5. Is it less than that one before 5? Yes, it is. Then move that one up and then put 5 down there. And it finds its position in the array as it goes along before it skips on and checks the next consecutive item. Okay? So the swap part, if the current item is less than my array j, so the one next to it, then my array j plus 1, so increment that. Give the value of j to my array j plus 1, so wherever j is, the next one along. J equals j minus 1, so decrement j again, so move it down left. My array j plus 1 equals the current item, so that is the swap that's made. Okay, that's it moving along and then moving that one down. That's that process. Okay, failing that, inserted was true, and then we continue on. Okay. So what I would do is I'd go and have a look on YouTube somewhere and try and find an insertion sort video that shows you the swaps being made, and then have the pseudocode in front of you and work out what's going on. Now there are multiple ways of doing an insertion sort. Now if that's not the method that you prefer from the exam board, that is completely fine. Nothing wrong with that at all, because there's different ways of doing it. However, you can write whatever algorithm you want. The examiner's got to run through it, and if it works, it works. They can't dock your marks for it. Now, what sort of questions do these things, what sort of marks do they bring in? About 7 or 8, 9 marks, but it's already been asked this. If you're talking about passes, Callum, I assume you're talking about the bubble sort. Swaps are made first, passes are made after. So then let's have a look at the quick sort. Okay, so the quick sort, remember, this is the most difficult one because it's a recursive algorithm. So declare sub-procedure quick sort. You pass in, well, this is what we were told to pass in the exam question. we pass in an array, a string array, okay? Now, you're starting to panic because it's strings. But that means that the array itself will just contain whatever it goes up to. It will just contain names, or letters, whatever it wants. Index low, index high is integer. Now, how does a quicksort work? Well, the pivot is a string. It has to find a pivot. Usually, you can pick whatever pivot you want. Usually, people pick the middle one and then separate everything out on its left side, on its right side. And then we find a pivot again. Then we separate out its left side, on its right side. Everything greater than the pivot goes on the right. Everything less than the pivot goes on the left. Doesn't get ordered as it goes. All we're doing is finding the pivot and sorting and organizing. We keep going, we keep going, and we keep going until we reach a base case. Okay? Base case, because it's recursive. Don't forget. So, temp swap is a string. Temp low is an integer. Temp high is an integer. Temp low equals index low. So index low is given in the question. So you can probably imagine that the low index is going to be 0 of some sort there. And the index high is going to be the highest value. And we don't know what that is because we're not given it. But we'll keep going. Pivot, my array, in index low plus index high. Now, there was an array given with the question, but I can't remember what it was. So, again, we'll just explain the code here. So, while the temp low, so while this one, down here, the value of that, the actual value, so 0 to whatever number, while that is less than or equal to temp high, keep looping. So, while these two arrows haven't met yet, keep going. Now, what's going to happen is we're going to move down like this, and we're going to keep moving these arrows until both arrows land back on the pivot point. When both arrows are the pivot point, we know we've been through and sorted everything from left to right. And that's the beauty of the quicksort. So it's super important that you declare this procedure and you pass it in these parameters, the array itself, the index low and index high. Why? Because you declare the procedure there. When you run this again, you declare the procedure here again, but pass it in only the pivot point minus 1, which will give you this one, and the index low. And then this one, when you call it again, you're going to pass in the pivot point plus 1, which will give you this one, and index high, which will give you this one. So by calling it again and passing it in specific pointers, yeah, you might pass it the full array, but you pass it specific pointers, which makes the computer only use the algorithm on the arrows specified by you. Okay? Bear that in mind. So, while temp low is less than or equal to temp high, so while they've not met, while my array at the position of temp low, my array, that's the name of the array, at the position of temp low, which is 0, is less than the pivot point. So the pivot, remember it's a string, so it's going to compare the data items, and temp low is less than index high. That is not comparing the string values. That's just comparing the numbers of what's being pointed at. Then what we do is we temp low equals temp low plus 1. So we increment temp low, okay? Because it's already on the left-hand side. So if we're looking on the left-hand side at temp low, if that is less than the pivot point, keep it there and just increment the pointer. It's in the right place already. Same thing on this one. The pivot point is less than my array at temp high. That's incorrect from the exam board. If the pivot is less than my array at temp high and temp high is greater than index low, then just decrement temp high because this is already higher than the pivot point, so just decrement this pointer. Them two are nice and easy. This one, if temp low is less than or equal to temp high, then we're going to make a swap. So if we need to swap them, temp swap, which is a string, remember, this is our temporary value again, is given the value of my array at temp low, My array at temp low is then given the array at temp high. So these things here literally jump over across the array and go down here, and this one goes up here. They swap over, okay? And then the swap thing, the swap itself is put in the right position. We increment and decrement the pointers because we've just moved them and they're in the right place, okay? So think about the conditions that we're swapping. If the thing we're looking at is less than the pivot, increment the low pivot. If the thing we're looking at is greater than the pivot, decrement the high pointer. If the things need swapping because it's less than the pivot, this is greater than the pivot, then you swap it with the thing down here. Now, in order for this to work, you need to do this call again. So if index low is less than temp high, then quicksort, then call the quicksort, my array, pass it the full array again, and pass it the index low now and the temp high. So after this, okay? After you've done all the moving and messing around, you then pass it the low pointer and the high pointer. If the temp low is less than index high, then quicksort my array, temp low, index high. So again, if you want to see this, I'm sure I did an exam video on this one because it was as part of your mock somewhere. Okay, so have a look on that and go through it again. That one is the most complex one out of all the sorts. Okay, it's quite difficult. Linear search. Linear search. The worst search going. Okay, but it works. It's good for small data sets anyway. Okay. So again, have you noticed all these searches and sorts start with an array? You notice that? They all have arrays. Why? Because it's so simple with an array. It's a single data type. So simple. And it also has an index which is easily accessible. So linear search, we'll go through it. Go through the array starting at the first position, move the way all the way through, checking if the search term is 0 at position 0. Is it there? No, it's not. Well, increment. Is it this one? No. Is it this one? No. Is it this one? Yes. Return it. Okay. If not, get to the end. Is this what I'm looking for? No. You're at the end of the array. Finish. So this question, declare an array from 0 to 6. So 7 elements in total. It says the search value is integer. Found is Boolean. Set found equals false. Input the search value. Input that number. So in pseudocode, input variable. We've declared it. Pseudocode is, not as, because that's VB. For I equals 0 to 6, so for loop all the way through the array, specifically 7 times. If the search value is at the position of I that I'm looking at 0, then it'll change to 1, then 2, then 3, then 4, then 5, and 6. Then set found equals true. Output search value found at position, comma I. End if. Next I. If found equals false. Output search value not found. Aminul, yes it does, yeah. The reason why the pivot in the quicksort needs to be the same is because the value, you're comparing the values of the items, not the index positions. So if you're looking for a string, then you've got to compare whatever's at index 0 as a string with the pivot, which is a string. So you're comparing the data items. So yeah, you do. Okay. So looking at the next one. This is it's technically the last one. Yeah, it is comp 1 column. Yep. Binary search. Okay, so the binary search has actually been included. I found it on a Welsh paper, not come up on the English paper yet. So here, what we're doing is you can do it in one of 2 ways. Okay, so you're looking for, this one is probably easier using loops. You have a lower bound and an upper bound. So the highest in your index, or in your array again. Let me get a pen. So your lower bound is 0 and your upper bound is your highest element. You're going to do while I low, which is your lower bound, is less than or equal to the higher one. Okay, so as long as these pointers haven't touched, or these two elements haven't touched, or they're not the same number, then we're going to keep going. Okay, I middle is your low plus your high divided by 2. So that gets you center 1. Remember with a binary search, you have to sort it first. You have to have it sorted. If the target, the thing I'm looking for, is the thing in the middle, then we found it. So if it's this element here, we've found it straight away. Exit the do loop, get out. Else, if the target is less than the data array, I middle, then I high equals I middle minus 1. So that means you decrement the middle pointer by 1 and you pass that as the high value. So it's this one here. Okay, so you're going to search just these two. And that means you've eradicated 50% already. Else, I low gets incremented. So you'd increment this one to this one and you would just search these. Okay? Now, you can do this recursively. Okay? This is what this one's saying over here. Right? So function, binary search is past the array, which is A. The search term, left and right, they are your pointers, lowest and highest. The mid is, they do it an interesting way there, really. They could just do it like this one here if they wanted to. That's much easier than all that garbage. If right is less than left, then return minus 1. This, if you've noticed, this is your base case. This is what's going to get you out of your recursive algorithm. Okay? If A mid, so the middle point, the middle of your array, is greater than the search term, then you return the binary search, you pass it the array again, you pass it the search term, but you pass it mid plus 1, and then the right, which means in your array, your center items there, you're going to pass it the upper bound, and you're going to pass it mid plus 1, which will get you this one, which means you get rid of mid, you get rid of the lowest stuff. Exactly the same as this one. This one's using iteration. This one is using recursive algorithms. Both worth 100% of the credit. Which one is easier? It's up to you. If you're happy with recursive functions, crack on. No problem with that at all. Okay, so you return that plus 1. Again, if it's less than, so if it's lower, if it's the lower elements you want, you do mid minus 1 and you return the mid function if you find it. Okay? And that's it. Use your binary search. So let's have a look. Maintenance chapter. What have we got? All right, let's do. George's asking for OOP, so let's do that one. Let's do some paradigms then, shall we? Make sure we cover these. Right. So 1.4 principles of programming. So Callum, you were asking. You're asking about. Maintenance and changeover. That all comes inside this stuff here. Look, maintenance, changeover, testing. That is a software development lifecycle. Okay. Oh, actually, I said I'll do an algorithm for George, didn't I? I will do that. So let's have a look at these then. Principles of programming then. Okay. Right. Let's make this quick. These are the principles of programming. These are the paradigms that you need to cover. All right. Now, a programming paradigm is the fundamental approach to developing programming languages or programming code, whatever you want. Okay. So this is the structure in which we program. All right. Now, lots of different programming languages make use of different paradigms. And don't be under any illusion that one single programming language can make use of one single paradigm. Some do, but some make use of more than one. Okay? So, in procedural programming paradigms, programs run from start to end sequentially, in sequence. Okay? Unless we encounter a control statement. So, things like repetition or iteration, selection, or a function or a procedure call, we're going to go from start to finish. That's what procedural language does. Okay? Now, what are they made up of? Inside the language itself, we have variable assignments, we have selection, we have iteration or repetition, loops. Modularity, we discussed modular programming before, so that comes under procedural programming languages. So that's all about splitting them up and recombining them later. Okay? Now, procedural languages, if you see it in your exam, sometimes they're called imperative languages. Now, if the exam board throw that at you, it'll be tight. Okay, it'll be harsh. So just be mindful of imperative languages are procedural languages. Okay, so imperative languages use statements to change the state of a program, and the state, that just means it's the current value of its variable at any given moment. So we're changing the values of the variables at any point in the program itself. Okay, so procedural programming is one of the simplest paradigms to learn. So usually it's one of the first that developers learn. Okay, speaking of the first thing that people learn, Scratch. Okay, Scratch is visual. Okay, visual is all about the syntax. Less focus on syntax, more focus on the logic of the program. It's very intuitive. It's very colourful. You use pictures and drag and drop in order to help you define what you want. Okay, you've all probably used Scratch before. It's probably one of the first things you've encountered. It looks like that. You spin a cat around. You put blocks in there. People can play. They can get things wrong. There's not a major need for understanding of the language itself. Okay, so Scratch allows characters and actions to be applied. It's done by dragging and dropping. It makes use of the event-driven paradigm. Okay, we'll more on this in a second. Okay, and it's all based on user clicks and interactions, and it's all about logic. Okay, dead simple. Now, event-driven and visual, like usually combined in games. So when you're games programming, that's what you mainly use. Event-driven rely heavily on user interaction. You've been using event-driven paradigms in VB.NET. Everything you see on the front end, your graphical user interface, you click, you drag, you drop, you double click, gets you into the code, etc. Then you start programming in a procedural fashion. Okay? So the point here is that the program will sit in an event loop waiting for the user to perform an action. And that's called an event listener. Okay? Now, the diagram I've shown you in the question, in the lesson, looks like that. The user presses a key, the operating system waits. We've looked at operating system interrupts, but that's on component 2. But yeah, we're waiting for someone to do something. Once someone has done something, then what we'll do is we'll put it in a queue. All right? So interacts, operating system deals with it, sends an event to the application event queue to action the code, and then once we're given processing time, we'll action it, and you'll see it on the screen, or something will happen. All right? So the listeners themselves are quite useful. Okay? And they're created by the developer, and they can be customized and made to do whatever you like. They sit in a nested loop structure, and it's literally if statements. It will direct you to whatever you need. So it'll direct you to select case statements in order to action some code. So event-driven languages, we see Python making use of it, Java, Python not so much, but Java and VB.NET mainly. Okay, they require the developer not to think of their code in a linear fashion, but rather as a set of actions triggered by the user. Okay, and they don't run one after another. They run when triggered. So things like when you shut down your computer, that is an event-driven application. You press the power button, it goes off. It's an event-driven application. It's driven by the event of you pressing that button. Right? You click any keys, combinations, shortcuts, etc. They are all event-driven processes. So your operating system is a graphical user interface driven by events. Okay? So like I said, games usually make use of it, and it's fairly common. All right? Now, programming languages. I'm just reading the comments again. That's why I stall. So markup languages are not programming languages. Yes, they are markup languages. The two main types: hypertext markup language and extensible markup language is XML. Okay, so markup languages are not explicitly programming paradigms, languages, but they're used in web applications or web technologies. So markup languages are all about adding comments and markup language to text documents rather to offer meaning to the text. So the commands are given instructions and then it's displayed as standard in your browser. So here is an example of HTML code. There's tags that are involved in there. So I've got my HTML opener and closers. The commands are shown with chevrons. And to close it, you do a / inside your chevron. And all these things, given examples like this, will get you marks. So commands like the H1 tag is a header tag. Title will be your title on your tab. Your P is a paragraph. Your IMG is an image, for example. These would all get you marks in an exam if you were asked specifically about this. And from there, all it does is provide meaning to plain text. That's why they don't need an official IDE that can be done in text documents and then they put onto a web browser and it interprets it as standard protocols would deem it to be looked at. So we've got XML, extensible markup language. This is used more for storage rather than display. Okay, so it's very similar to HTML, but we have customizability. So you can customize the commands in order to make up what you want. So there's an example for you. We made something called a headline. We've made something called news. Those tags there are made up by us, story, etc. And that provides extra customizability, extra functionality, but it's made for storage. We're storing data usually with XML. Okay, so markup languages, both XML and HTML, are usually combined with other languages to give it some more power. So JavaScript is the main one it's used with now, and CSS, cascading style sheets, to give it some information, some more information, more color, text, style, programmability, interaction with databases in the back end, etc. And that gives it. That's why websites are still being used now. So we still make them in HTML. We use JavaScript and PHP with them now, and CSS. Okay. There's something called non-procedural languages, which I remember going through, that weird, scary freak robot thing. They were originally created for relational databases. Okay. And that means they focus on solving the problem. They don't care how it's done, as long as the problem's solved. So they concentrate on defining the input and output, what's going to be put into it, rather than the steps of solving a problem, which you're not used to. They're known as declarative languages, and they focus on rules, facts, and queries. Queries comes from databases, to query, to ask a question. And this computer language does not require writing in the traditional programming logic. It's used in AI, artificial intelligence, grammar, and language applications, because it has to think about things in an abstract way rather than a set procedural step-by-step process. That's what it's focusing on. Then we've got object-orientated language programming. So this is a popular one, used all over the world, very modern, very sort of class separated, matches the modern world using objects. And you can understand the basics of procedural languages. If you can understand that, then you're probably going to move on. Your next steps will move on to object-oriented languages because it's better. It's all about reusability of code, okay? And we get lots and lots of support. We get programs that are well structured, and we get the potential for reusable code. And that's really the main reason I use it, because everything's done in classes and I can just reuse classes and things like that. Okay, so looking beyond that, it still uses selection, iteration, assignment of variables, identifiers, and constants, all the standard stuff you get with your programming language. That is all fine. You also get some differences. So procedures in procedural languages, they're replaced by classes, objects, and method. Methods, okay? Methods, think of methods as your procedures and functions, okay? Objects stem from classes. So you have subclasses. We usually class them as objects, but objects hold methods and attributes. That's what they do. So it's all about offering modularity of code, like we talked before, about people splitting up and sharing tasks. So classes allow the developer to produce more reusable code and relate their design more closer to reality. Okay? So there's characteristics in object-oriented languages that you need to be aware of. And now these could easily be asked. They've not all been asked yet, so these could easily come up tomorrow. Encapsulation, which is a method of hiding. It's the public and private. We've got polymorphism, the method of overriding. Inheritance from classes, like genetic inheritance from your parents, it's the same. Classes and objects all provide reusable code, and abstraction is all about removing the complexity away from the user. Okay, so objects, classes, and methods then. Yeah, I will do timestamps there, Shaq. No problem with that. I'll do timestamps, no issues. So objects, classes, and methods. An object is a combination of data and the actions that can operate on that data. A class is the definition of an object. So it's defined of an object. So it embodies all the information needed to create multiple objects of a particular type. Okay, so here the car is a class, whereas Jaguar, Ford, Aston Martin are all examples of objects. Now, the methods that we have, our attributes are our variables and our methods are our procedures and functions. So methods are fundamental. They are the behaviors. In your Tesla car, you'll have a method called turn left, for example. That'll execute a left turn at a certain angle at a certain speed, for example. And that is just called. How many left turns would you do if you were traveling in a car on your way to work or whatever? We won't have to redefine that code over and over again. We'll just call it once and it's job done. Okay? So when we create the objects, we use this thing called instantiation. So you were all instantiated from your parents. You were born from them, from your mother. You were birthed. That's what instantiation is, and you inherit everything with instantiation. Okay? Attributes. To set an attribute of a class, you need to use the reference created during instantiation. So here is an example of that. The Ford. This is the car class. It's got everything in it, all your methods and all your attributes. When you do Ford equals new car, you instantiate. You are born from it, Ford. Okay, and everything is passed between those two things. Then you can set the reg number. You can set the make, the model. These are all different attributes of the car class. And you just use the dot like we do in structures. And that will allow you to assign data. Then you can print it out. Just like that. So this is instantiation. Okay? So you can assign attributes and use them. Each object can have its own, so you can add in specifics. So when I did this example, I said my car can park itself, whereas an Aston Martin can't. So that, even though we have all the same attributes, such as the number of doors and number of wheels and engine top speed, etc., that is all set as a part of the car class. Specifics can be set locally in my class, so I can add extra functionality. Encapsulation, it's the technical implementation hidden within the object. So it's the hiding of the implementation of a class and controlling access to its methods and attributes. Classes can hide how they work from the developers. So you might not want other developers messing up or dealing with certain things, so you can encapsulate your code and it will all be hidden away. So usually we use public and private to do this in object-oriented programming. Then we've got inheritance, which is very simple. It's the same way that we use genetics in the modern world. So when you're born, some things are passed down to you, to your genes, and it follows the same principle. So inheritance works like this. A car and a van have all common functionality. We want to take that functionality and put it inside a superclass. Okay? that goes in there. Car and van. All of them, even though they look blank, they all share all of these things up here. Polymorphism. It's a pretty difficult one to understand, but it can be made simple. We've got polymorphism gets used like this. We've got A and A plus B, and then I said or then because I'm thinking of Boolean algebra. A or B, just did it. A plus B, so they're integers. If we're doing a plus, it's an arithmetic operation because they're both integers, whereas if they were both strings, it's a concatenation operator. Concatenation just means putting the two things together, like cat and dog, it'll be cat dog. Now, how does your system work that out? That is all written in your object-oriented programming paradigm. It's written in there. So it overrides behaviors, whereas you do an arithmetic operation, depending on what's been inputted, it will change its behavior. So poly, many forms, polymorphism. Okay? Abstraction. Remember, I used my car as an example. I don't know how it works. I ain't got a clue. But I know that if I turn it on, press the button, and then I start driving, I press the accelerator and put it in the right gear, it will go. So I don't need to know what's happening. I don't care what's happening. This is all hiding stuff. It's all hiding information away from you. All the programming you've used ever, something has been abstracted away from you. Something. Okay? And that is all your paradigms in a nutshell. Okay. Let's just quickly, someone asked for this before, I'll just quickly move on and do Backus Naur form. Okay, Backus Naur form. Nice and quickly. So, Backus Naur form. Those two people have caused you this problem. Okay? John Backus and Peter Naur. It's a method of grammar. Remember, we used it in the compilation process. It has non-terminals, terminals, and production rules. So here is a non-terminal digit. Remember, colon, colon, equals, and then you have your terminal itself, okay? The terminal can't be defined any further. That's what terminal means. A non-terminal digit means it can be defined further. So we go inside digit and we say, what is it? Digit is a 0, it's a 1, or it's a 2, or it's a 3, or it's a 4, or it's a 5, or it's a 6, or 7, 8, 9, 9, okay? They're all separated by a pipe, okay? The pipe symbol stands for OR, all right? So make sure you get your syntax correct. Rules are written inside chevrons, okay? So that's what we're talking about. Symbols and characters, digits. They are all things that are created as rules, okay? Now, the OR symbol, we talked about that. If terminals or non-terminals are next to each other, that's fine. You can have JBR, they're all terminals because they can't be expressed any further, and you can have a rule. That rule would state that JBR can have a digit of 0, or a 1, or a 2, or a 3, or a 4, or a 5, or a 6, or a 7, or a 8, or a 9. This is called concatenation. So remember this, said about concatenation before, it's putting it together. Okay? So rules, they can be combined together. A two-digit rule can be combined inside a rule. That's fine. Now, if we kept going with that, it would be an issue. Recursion always gets you a mark. Okay? If it's possible to define a single rule that can define any number of digits, then there can be a recursive algorithm for that. Now, what we see in exams now is the null rule. Let me just add that in. Okay? This will say null or digit or digit number. Okay? Now recursion, remember, it calls itself within itself. So if I finish my rule off and do it properly, dot dot, and I do number, Null is your base case. It means you don't have to take anything. You can back out the rule without doing anything in there. Okay? Digit, a single digit on its own, or a digit and a number. Okay? A number means that you go all the way back to number and you do the rule again. Okay? So you can take a digit and another number. So you go back, you can break out, single digit, another one, and another number. Another number. And you can just keep going. That is recursion. Okay? So Tanvir was asking about this before. Your symbols. This is your symbol, your syntax diagrams. So for my digit rule, my sign rule, sorry, this means you can have a sign consists of a plus or a minus. Okay? So you can have an option to break off and go for a plus or a minus. Your non-terminals, go back a second, your terminals are in an oval or a circle. Doesn't really matter. They're not specific. They don't really care about if you leave the lines on or off. It doesn't really matter. But your flow must have an arrow to show you direction. Your oval or circle is a terminal, which can't be defined any further. And your rules or your non-terminal symbols need to be in a box. Okay? So that's what that's saying. A plus and a minus can't be defined any further. Therefore, they're terminal symbols, and you can have one or the other. Okay? Concatenation, just put it on the same line, 2 digits together. You can have recursion. So recursion, doesn't matter if you draw it from the digit box, but you would draw it usually before or after the line, which means you can go back and you can do it over and over again. So you can have a digit, or another digit, or another digit, or another digit, or another digit, etc., etc. Okay? And that's that. Now, what are people saying? Because time is ticking. Null, yeah, I would include null because you need a base case to break out. If you forget to do it, I can't see you being penalised an awful lot for that, okay? I've not seen null get marks on mark schemes, so I would say at this point, it's not real. If you can remember it, do so. If you can't, then that's fine. Don't worry about it. I wouldn't spend too much time on it, okay? So I'll quickly just go through some pseudocode for George was asking before, all right? Let me just make a... Right. This is the sort of thing that you're going to be up against. Okay? It's an algorithm. I will quickly go over case tools, Morum, don't worry. So what's actually being said in this? It gives us a written algorithm, and we have to turn it into pseudocode in order for it to do something. Now that's not completely unrealistic. Okay, you will get given a situation. Usually they're looking for you to create ranges, means, find odds or evens. They want you to do some mathematical calculation to pseudocode something. Now there's a big disparity in students with this. Some students can do it and some students can't do it. Okay, there's no real in between. Now, you've got to apply logic to this as much as possible. All right? Now, to do this, let me get my pen. A sales director of a company wishes to compare the sales in thousands of pounds achieved by her sales staff in the previous month. Design an algorithm using pseudocode. Now, it can say using a recognized convention. If you're happy with flowcharts, you could do this as a flowchart if it said that. If it specifically says pseudocode, then do it as pseudocode. There are a few different methods for representing algorithms. Pseudocode, structured English, and flowcharts are usually the main three. Okay? So design the algorithm with the following inputs: the number of sales staff, sales figure for each member of staff. The algorithm should output the mean, the values of the sales figures below the mean. how many sales figures are below the mean and the lowest sale figure. For instance, 6 people, one person got 45, 55, 65, 65, 10 and 60. The outputs should be mean 50, values below the mean are 45 and 10. The total number of values below the mean is 2, lowest sales figure is 10. Okay? Okay, right. So, if we're not given an array in the question, we have to make it ourselves. All right? So you can say now you can write declare if you want to, or you could just write sales array. I'll put array. Should have made it shorter to say writing, but hey, sales array, and then whatever you put, the brackets after it indicate to me that you are wanting an array. Now, what do you want it to? If you want it very, very large, you can put 1 to whatever you want. 9999999. Do as much as you want. Okay, that's as big as you like. Now, as what data type? Well, I want integers because I'm taking in numbers. Okay, as integer. Okay. Now, what I want to do is I'm going to get marks for declaring Callum, I wouldn't recommend doing structured English and pseudocode together. It gets very confusing. If you're really struggling, then yeah, but don't. Try not to. I use set to set a variable. So set total, and I would say, well, what data type is it going to have? I can set total as an integer, and then I equals 0. Now that is assignment and initialization on one line. Okay? So set the total as integer. Setting is this assignment. As integer, that is making a new variable. All right? Then we have to set the minimum. Set min. Again, as integer. Equals. Now, this has to be a really high number. In order for me to set the minimum, it has to, whatever I check it against the first time round, it has to be lower than the minimum to set it first time round. If I set that to 0, then if I come along and get a number 45, which is the first number, and say, is that the minimum? Well, yeah, it is because it's the first number. But if that's 0, is 45 less than 0? No, it's not. So it's never going to set the minimum properly. Okay? Now, set number of, I'm going to call something number of lows because I want the number of low numbers below the mean. As integer equals, and I set that, 0. Okay. And then in pseudocode, if you want someone to put something in, they input number of staff. Now, why am I asking that? Num staff? Because they input the value of 6. Okay? So that's just entering the number of staff. I've just abbreviated it. Okay? Now we want to loop each one. Now, if we've got a specific set number, like 6, for example, we know we need to loop from 1 for count equals 1. Here's my counter. Count equals 1 to num staff. Now we don't know what that is, num staff. That's up to the user, so we can use it freely like this because it's whatever they input. All right. Then we need to put that input. We need to ask the user to input the sales at the position I've called mine actually sales array, haven't I? Sales array at the position of count. So what is that actually doing? Here's an array. It's called sales array. Inside of it, it has values 0, 1, 2, 3. Position of counts 1. So 1's here. It's going to put in, someone's going to input a number in there. The first one's going to be 45. So it's going to go in there. Okay? That's what's going to go in. All right? Now then, input sales array at the position of count. We need to add this to the total. So we set the total. If you want to change the value, you got to say set the total to equal total. Oh, make sure it's me, my sloppy pseudocode. Total equals total plus sales at the position of count, because we've just put it in there. And it's not sales, John, it's sales array. Sales array at the position of count. Okay. Fahim, I don't need to set count. No, because it's been declared in my for loop. So looking at set total equals total plus sales array, that's going to keep count of my sales. Then I'm going to say if the sales at the position of count, what am I looking for now? What am I looking for? So I'm starting to do the minimum. So if I set the minimum, if it's less than the minimum, if then min, not min, sorry, yeah, min. So I need to set the minimum to equal sales at the position of count, because that is my new minimum. This will keep a constant check of my minimum. Then, don't forget, end my for loop, end if, sorry, and then end my for loop. Or you can say next, let's say next count, because it's going to increment, isn't it? Next count. So that is all going to happen inside itself there. Now, let's work out the mean. I'm going to set the something called the mean, which I need to create. Set mean. What data type would I need for the mean? If I'm going to divide it, and I might need a real. Equals the total. So total I'm going to take divided by the number of staff. Num staff. Now this question, if you think about, like, this is a lot of work. This, I believe this would be worth more marks now than it was back then. Okay. Oh yeah, sorry Shaq, yeah. Pointing that out there. That should be count. Always on the ball. I hope you're this on the ball tomorrow in your exam, Shaq. Okay, so let's count. Now, this would actually be worth, I would imagine, about 8 marks in an exam. It's asking you to do quite a lot of things here. I'll go through the marks for this, where you get given them at the end. So I've done the mean now. I've done that. Now, it wants me to output the mean, so I might as well do that while I'm here. Output, which is the word you use to output things. There's no message boxes because that's VB. There's none of that stuff in pseudocode. So output, now here's a top tip. You need to have something meaningful. Okay? When I say something meaningful, if you just output a random number, which you know is the mean, on my screen, I am not going to know. Okay? So you need to output an actual message with it, and you can output it, a message. In speech mark shows me a message. The comma shows me you're adding to it the mean value. Okay? Now then, I need to find out, now I know the mean, I need to find out the number of looking at the thing there, looking at the number of integers that are below the mean. And now I know the mean. I'll just come out here. I'll just come over here for it, and so I've got more space. I'm going to loop again. Okay, I know I can loop for everything, so I will do. For count equals 1 to number of staff. Again, let's loop through my array. Num staff, there's nothing new here, nothing new. So I'll loop through each element in my array. If the sales array at the position of count is less than the mean itself, the mean value that we now have, then what am I going to say? So it's less than the mean. Then we set the number of lows. Did I call it num lows? Yes, I did. Num lows equals num lows plus 1. Taking this very steady, going through question by question. Can I now output the mean? Yes, I can. About the values of the sales figures which are below the mean. That's what I'm doing now, okay? How many sales figures are below the mean? How many is this one? And then I need to output the actual value then, don't I? Okay, so output, I'll give another message. Num below mean. Output sales count. Sales count. Okay, so that's going to output both of those two bullet points. The value, so I've output the actual value, and then how many. Okay, I haven't actually outputted how many yet, but I will do. I need to end the if first, because we need to loop through them all and count them all up. End if, end for, or next count. We'll do next count again. Next count. Okay. Wonderful. So apparently I've still got 19 viewers doing overtime. Wonderful. So what else have I got to do? Just need to output the rest of the information. So output, after we finished all that looping, output total below mean equals, concatenate that with a comma, and that is num lows. Num lows, and then the second one we need to do, output the lowest sales figure. That's the minimum. Output lowest sales figure. And then that's the minimum. Okay, you can output individually in output So I've got one output, two outputs, three outputs, four outputs there. I've got the four outputs there. So I'm just going to check this again, make sure this is all correct. The algorithm should output the mean of the sales values. So I've worked out the mean there and I've outputted that. So that is that one. I've got the output the values of the sales figures which are below the mean. So if set the mean, output the mean. I've got this one here, which is if the sales array count is less than the mean, then output that. So number below the mean, sales count. So that's that one. It's the value itself from the array. Then I've got how many sales figures are below the mean. So the total number of sales below the mean. So that's me counting up my num lows. That's been outputted down here. And that's that one. And the lowest sales figure. So the lowest sales figure itself, which is the minimum value. So every time we go through, calculate the minimum value, checking if 45 is the minimum. Check if 55 is the minimum, 65, then 10 will get set to the minimum and that will get outputted. Okay, so we've got them there. Okay, the outputs can be done wherever you like. You can concatenate them all together, but there we are. So the marks you can get for this, like I said, this will be worth more now. This is an old spec question. Initializing, declaring inputs, initializing, declaring variables, that'll get you a mark. Your inputs will get you a mark. Your loop structures will also get you a mark. You've got your updates, so updating values, minimum values and things like that will get you marks. Any mathematical calculations also gain you marks, so mean values, ranges, most frequently used, maxes, anything like that. Outputs with speech marks and give value, they will also gain you marks and credit for this. Okay, now there's no marks given for elegance. There's no marks given for efficiency. It doesn't matter how you do it as long as it does what it says in the question. So it can be, you can have hundreds of loops if you want. You can have hundreds of separate if statements if you want. It doesn't matter. As long as it works, you're going to gain marks for it. Okay. So I will timestamp this off towards the end. What did Maureen want? She wanted case tools. Okay. I'll quickly go through case tools then. Let's have a look. So quickly run through software engineering then, because it's literally two things. IDE tools and program version management are the sort of key areas of this. However, there's case tools involved in there. So what is a case tool? Computer-aided software engineering. In the AS paper, we got asked about utility as well, utility software. So be prepared to talk about, well, standard utility software basically. So some students looked at the paper that were in lesson. I give them the AS paper and they looked through it. It's a fairly decent paper. So computer-aided software engineering, it helps assist with design, development and testing of software, and it's partially inspired by computer-aided design. So what comes with case software, okay? Computer-aided software engineering, what comes with that? So we can get things like data dictionaries. It can help us design and develop diagrams for production, code generation, automatic code generation, like from what we get from our IDE, providing repositories for reusal of code, like modules and things like that, providing project management tools, version control, so some people involve Git and things like that inside it, carrying out report generation, include prototyping tools and testing tools and things like that. So with case tools, we've got two main categories really. We've got uppercase and lowercase tools. Think of it like you've got analysis and you've got development. So planning, analysis and design are all a part of like the sort of getting ready to do something. And then you've got the bottom part, lowercase tools are all for actually doing the thing that you wanted to do in the uppercase element, okay? So your uppercase tools, you've got diagram tools, process modeling tools, project management tools, documentation tools, analysis tools, and design tools. In the lowercase stuff, you've got configuration management, how you can actually configure the system itself, you've got the control tools. We've got programming tools, prototyping tools, web development tools, quality assurance tools, and maintenance tools. These are the things that are going to be included in your IDE and things like that. Most of these sort of crisscross a little bit, but there are specific software for design of diagrams and project management and time and version management. Whereas the lowercase tools, really, they're all inside your IDE mostly. Okay, so the planning tools, we've used draw.io and things to create diagrams. Allows us to generate diagrams quickly. Doing it electronically is a whole lot more straightforward. It's dead simple to edit and change things in there. And you can also print them off. You can send it to people. Collaboration is easier. You've got analysis tools, very complex and involved process. We know how to analyze, don't we? So in our software development lifecycle, we know what has to go in there. So you can find and record the requirements of use cases. So what do people actually need? You can record all that in there. Also test cases. So what do we need to test, or what will our software do in order to test? So we want to make sure we set our tests up before we actually develop it, so we have goals to meet. Then we've got design tools. So looking at this here, we've got use cases are something that they are a list of actions or events or steps, typically defining the interactions between the role, which is the user, which is us. We're called actors, and a system to achieve a goal. So what processes need to take place in between the front end user and the back end system. So if you look at this diagram up here, we've got somebody using a credit card system. They can do all these things. So in between, someone can authorize, capture, credit, void, etc. in a bank system. And then on the other end, what does the bank system actually need to do to interact with these processes to give something to the user? Okay, so that is a UML diagram. So lowercase tools, you can get them for doing that. You can also get them for wireframing. And the good thing is, management's much easier. You can also quickly edit, like I said before. So design tools allow systems to be modularized, ready for implementation. So you can split this up, give it to your team, come back in 2 weeks, show them what you've got, and you've all used the case tool to do it. And you can also share things between that. So tools help prototype interfaces. You can get a quick snapshot. Sometimes the customer likes to know what it's going to look like in a design form before it's actually created. And if we edit it now and get the customer happy with it, then down the line, it's going to be much easier to implement changes earlier on rather than at the end. Okay, so that's wireframing. System testing is a massive, massive help. So automated testing tools, written test plans, bugs tracking. We looked at Launchpad, which is a piece of software that allows you to sort of report bugs and potentially fix it using the software itself, but it can provide help with testing and keeping your test logs. In your coursework, you all did manual ones, so you did your table and you generated your tests with different kinds of data, valid, invalid, erroneous, etc. This does it all for you. Okay, so you put in your parameters and then it'll run your tests for you. The maintenance of software. Modifications in software occurs once the software has been delivered to the customer. So it'd be helpful to the developer if the software recorded what it's been doing while it's live and running. So this is like when Microsoft send you analytics and they want you to send things back to them, and it will send them like auto login error reporting, auto ticket generation, root cause analysis. If there's an error or there's an issue, it'll send that back to to Microsoft, for example, and then they can look into it and fix that and send out an update or a patch for their software. So the good thing about case tools is that you get an increased speed throughout the software lifecycle because it helps you do it. Okay, we all know how boring the software development lifecycle is, but it helps you get through it faster. Increased accuracy in software production because it's more documented. Reduced lifetime maintenance. So that's good and bad because we usually maintain it and get paid for doing it. But reduced lifetime maintenance. That means we don't have to we can give them a better, more robust piece of software. Then we've got better documentation, programming in the hands of non-programmers. So we can give basic functionality, like Cedar has basic functionality for our sort of web person, John. He will use the basic functionality to program things into Cedar that we want, so to customize the functionality. Bad thing is, if we have individual tools, they don't always link up together, and we've got to learn each individual tool. So if we want a Gantt chart for helping us order things, then we've got to work out and learn how that Gantt chart software works out. If we want bugs tracking, then we've got to work out how to do that. If we want GitHub, we've got to learn how to build that in, and you've got to learn all that stuff. So costs also come with specific pieces of software. This is from a mark scheme. So Case Tools is a software tool which provides a number of functions which assist with the design and testing of a computer system or program. Provides a data dictionary, graphics and diagram production, repositories for reusable code, program management tools, version control, report generation, prototyping tool. Just focus on what are the good points about prototyping. Rapid prototyping is good for agile methodology. It's good for quick editing and reduction in costs, especially with our built-in physics now. So we can do strength testing, and for bridges, we can do virtual reality modeling. People can walk around it in a virtual environment, etc. So prototyping is a very powerful or empowering tool. On this software development section as well, we've got integrated development environments. So IDEs, Visual Studio, come with lots of features and functionality. We've got coloring of syntax. So our red for strings, comments are green, keywords are blue, etc. That helps you read it. Helps me read it anyway. We've got automatic line numbering. I can tell you what line number the error is on. We've got link constructs. So if I write if and write something, press enter, it'll create the then part, and it will automatically indent it, and it will create the end if part, all for me, so I don't have to do that anymore. So it structures my code for me. I've also got highlighting. So it will highlight things that are incorrect. It will show me squiggly lines underneath it if something's not quite right. We've got debugging. So running, breakpoints, during runtime, automatic error checking, and error reports. Breakpoints are very valuable. Stepping through code is one of the key advantages of IDEs. And we've got version management. So version management, you might see a number, 1.1, 1.2, 1.3. And they increment, they're sort of minor changes. The main changes will come on the 1 to the 2 to 3.0, 4.0, 5.0. They're major changes. The release year would also come with it. And sometimes people put in their own codes as well, in order to help them out. Okay, so that's sort of a nutshell of software engineering. I'll see what else people are wanting. Everything easy if you talk about it. It's a shame the exam isn't spoken, Shaq. If you look for the grade boundaries in Google, you'll find out how many marks for a pass. I'll just do a quick search. Now, we can't be sure on the 2019 science one. So depending on what your coursework grade was, component 1's out of 100, component 2's out of 100, they get doubled. So looking at computer science, in order to just pass the exam, you need 39 out of 100 in your coursework, and 25 and 21. So 25 in the component 1 exam and 21 in the component 2 exam. And like I said, they get doubled. So if you get lower on your coursework, or you have a lower mark in your coursework, then you have to obviously to get more in the component 1 or the component 2. But for an overall score, you need 131. So that's component 1 doubled, component 2 doubled, add your coursework, and 131 is your lowest score you can get to pass the exam. Okay. One more thing. one more thing that I'll go through. Just looking at the exam questions section, people were asking me about predictions. Very hard to predict, but looking at data structures. So we got asked about binary trees and binary tree traversals. That was the specimen. We got 2017, a binary tree came up. 2018, stack data structure came up. Now, 2018, question 11, we had a binary tree again. So each year, binary trees have come up and we've only been asked about stacks. That means that queues can come up, linked lists can come up as well. So that's where I'd be focusing my revision on those areas, because they do like to throw in a data structure question. Logical operations, it's highly likely a Boolean algebra, almost certainly to come up, a Boolean algebra question. They started to ask about now, looking at masking, encryption, and clearing registers. That's important. So 2018, they give the Boolean identities. So they got you to complete the Boolean identities. Then you got you to do a Boolean algebra question. But in 2018, there was nothing on masking, clearing, or encryption. Okay, so that might be something that will be asked. So remember, masking is using the AND operator with a mask. We've got clearing, which is using an AND or an XOR with the same data, or clearing ANDing with 0, and then encryption is using the XOR with a key. Okay. Then we've got algorithms and programs. So because it's a massive topic, what did they actually ask on this one? So an awful lot of stuff. 2018, loads of questions on it. So in 2018, they were talking about main stages of program production between investigation and that take place between the investigation of an existing system and the carrying out of acceptance testing. So they asked for specifics in the software development lifecycle. They asked for maintenance. Now, changeover was asked on the AS paper this year. And other than that, that was it. So there's loads of things that they could ask. And they asked a big 15-mark question at the back of the paper on that in 2018. Sorry. So lots of things could come up in that section. System design, they've asked nothing on system design yet, as far as I'm aware. Okay. So principles of programming, Backus Naur form seems to be a popular route that they tend to go down. In 2017, Backus Naur form. 2018, they asked procedural languages. One thing I would touch up on is looking at just making sure you can definitely do Backus Naur form, because that's where they seem to go with these questions each year. Backus Naur question in that section. Principles of programming. Then you've got systems analysis. So this software development lifecycle, they're asking lots of stuff on there. Software engineering companies asking questions on that. IDEs, modular programming, systems analyst, feasibility studies. I think you're all quite comfortable with that, and if that comes up, that won't be an issue. Software engineering. So like I said, system design, there was nothing on system design. So system design is HCI, design, validation, and evaluation. So quickly, HCI, command line interfaces, text-based, very difficult to do, responds very quickly, but it's not for novice users. It's definitely for expert users that know commands. Graphic user interface, well, yeah, menus, pointers, icons, intuitive to learn. Forms interface, well, usually develops as part of the GUI. It's for getting input-output for the system, really. Registering email accounts, getting people to enter in. And the form interface, a form is what people write into. So contemporary approaches to this. how the interface has changed. We've got voice input, touchscreen, force feedback, virtual reality, and augmented reality. Natural language interfaces are how we speak or deal with. It's our natural language that we speak in person and how we can talk to a computer and it will work out what we're doing. So we've got voice input, specific commands. Now, don't mention Siri, Cortana, Alexa, Bixby, whatever, in an exam. All right, talk about a smart mobile phone. Talk about a smart system, a gaming device. Don't be specific about those. Voice input. Well, we know about the disadvantages, complexity and ambiguity of the natural language, people's accents, background noise, phrase commands differently because it doesn't understand it. That's the problem with that. But the good thing about voice input is that it's good for disabilities and disabled users. Touchscreen, two types, capacitive and resistive touchscreens. Capacitive, make use of your human body, your electrical conduction, allows for multiple touches at the same time and gestures, so swiping, etc. But pens don't work usually, and they are intuitive, very intuitive for young people especially. Okay, force feedback, haptic feedback it's also called. So vibrations in order to tell you. We looked at different people wearing bodysuits now that will give them haptic feedback and things like that. Apple brought out their haptic feedback for most of their touchscreens and their capacitive buttons. It is expensive, and it's starting to become more well supported now. So virtual reality is taking over as many senses as possible, enabling them to navigate through the world in an intuitive way. And the difference between augmented reality and virtual reality is augmented reality overlays virtual elements onto a real environment. Virtual reality does not do that. It takes over as many senses as possible. So we saw this in Pokemon Go and the HoloLens in augmented reality. Okay, different areas where it's currently being used in travel and tourism, manufacturing, education and training, and retail. It'd be really nice if they asked a question on this, augmented reality and where it's being used currently. And then you've got system design validation. So it's the process of testing carried out to make sure that our products have met the specification, basically. Okay, so we've got those 5 requirements. So does it meet the functionality set out? Does it perform in a timely manner? There's actual time specified for use of systems. Robustness. Will it work if lots of users use it, for example? Is it under budget, over budget, on budget? And is it usable? So can people use it for the skill level defined? Okay. Design validation and evaluation. So design validation, checking that the solution being designed and developed is the best solution available given the resources. And you've got design evaluation is a detailed examination of the positive and negative aspects of a solution. Put simply, is it any good? Okay, so there's no questions asked on that so far. Who knows what's going to happen tomorrow? Okay, software engineering. Compilation process really. It talked about 2018, code generation, optimization, identify tables. Section 9, to give an example on the SAM, on the specimen. Okay, so what I will do is I will send out this resource that I've developed for this, so you can actually go through it and just recap and look at it. So Tanvir is asking for Mantis as an exponent and things like that. That's on the next exam. So if you're doing that tomorrow, I'd be very surprised. So let's look at compilers. Not compilers, sorry, what am I about? Compression. So let's back over to algorithm programming. So compression for Tanvir. Okay, the first step is basically explaining what compression is. Then it's reducing the amount of file space. So you're trying to take a file and make it smaller, but why do we do that? We do it for sending over a network, mainly because bandwidth is expensive, not financially expensive, but storage on secondary storage devices, you might have to buy a secondary storage device to fit more data on it, so compressing it's a good idea. If you're sending it over a network, then you might want to think about the cost that you're going to have. Nowadays, it's very, very cheap to buy memory, so we don't really care anymore, but we still compress things. You may be expected to calculate a compression ratio. Okay, so that's the size of the compressed file divided by the size of the original file. That will give you the compression ratio. Okay, so the ratio will be a number between 0 and 1, and the closer the ratio is to 0, the tighter the compression is. Okay, so the more towards 0, the better it's going to be. Okay, so the different pieces of compression software, we've got WinZip, WinRAR, 7-zip, etc. They achieve slightly different compression ratios in different data sets. So you won't be expected to talk about WinZip, WinRAR, 7-zip, but bear in mind. So lossy and lossless, depending on the quality of the stream, lossless and lossy are the two main ones, especially you cover them at GCSE, but what is lossless? Well, you don't lose information, do you? It's never really used for images. It's more used for textual data, because lossy is terrible for textual data. It's used for images, okay? So lossy compression tries to remove the number of bits and pixels that are in an image. So it tries to remove things that are not apparent to the human eye. The more you crank up the lossy compression, the more pixelated something will become. Whereas lossless will use algorithms to reproduce it exactly as the original intended. So you've got run length encoding, which is used in things like DNA sequencing. So in some files, a single character will be represented a number of times in the row. So we try and get rid of that as best as possible. So run length encoding replaces a sequence of repeated characters with a flag character, and then it's followed by the character itself in a number of times repeated. So for example, all them B's there would be $, which is your flag character, B9. Okay, so that means you're going to have the flag B's repeated 9 times. Okay, now if it's any less than 3, like 3 B's, we wouldn't put $B3, because dollar is 1, B is 1, and 3 is 1. That doesn't make sense. Like, it's just exactly the same number of characters that you're storing. So anything less than, or anything 3 or below, we don't bother with. We just leave it as the original. Okay, so there we are. Dictionary encoding is another form of lossless compression. Dictionary of commonly occurring sequences of characters is created, and then the most frequently used are given the lowest number of bits, basically, and then the references to them are shorter than the words that they replace, so that saves space, basically. All right, so creating a dictionary is simply a case of scanning the document to find the most commonly used words and assigning a reference to each of them, and the reference is shorter than the original data stored. Huffman encoding is another method of lossless data compression. So the idea is to give a variable a code, okay, and then the most frequently used again have a smaller code, and then we put them in a tree, we traverse the tree. So in this, let's say we were trying to transfer pineapple and banana, we remove repeated characters, and then what we do is we give each one of those, all those letters there are needed, we give them a value. The only problem is, once we give them all a value, then we run into a problem like this. What if the message sent was 111? What does that mean? Is that a P and an N? 1 and 1 1? Or is it an N and a P? Is it a 1 1 and a 1? Or is it an underscore of 1 1 1? So we need to work out what that is, and it goes into our priority queue. So you don't really know any further than this at all about Huffman encoding, but there's 3 steps. The priority queue detailing the frequency the letters occur, so how frequent are those letters. They create a Huffman tree to show how frequently used they are, most frequently being at the top, and then we'll traverse the tree, okay? Least frequent to most frequent. And that's it. That's Huffman encoding. So comparing, compression. So when you're comparing them, you need to consider the following factors. So is it important to note that it's not worthwhile comparing lossy and lossless algorithms with one another, because lossy will always reduce the file size more than lossless, and it will also be a better quality. The compression ratio, we need to know what that is. Compression, decompression time. How long does it take to actually zip a file up? How long does it take to decompress it at the other side? If that is not shorter than the time it takes to send it, then what's the point in doing it? Okay? Something called a saving percentage, a percentage measure of how much smaller the compressed file is to the original. So what's your percentage of saving? Okay? And that's it for compression. Okay? As far as I know, I'm not doing another live stream for component 2. Okay? So we'll start finishing up now. If you have any more questions from now until tomorrow, do email me. I will send this out in a minute and I'll timestamp it up. The things that I'd be looking at revising is chapter 9. Chapter 9, chapter 6. Chapter 9, chapter 6. I would definitely go over Backus Naur form, make sure I'm happy with that. You can see the big O notation questions on my YouTube channel. Dijkstra's algorithm, I would look at that. I would just make sure I'm happy with my sorts and searches before I go into the exam. The Boolean Algebra. If you go through this presentation that I'll send you, what I've done for you is, if you're still unsure about Boolean Algebra, I've put a few questions on there because I think Tanvir asked me for some. I've put them on, going through them, and it takes you through step by step. Okay, so I'll send you this and you can go through that and work out what the answers are and see if you can get to it. What I would do is I'd probably have a go trying to get the answer first. Okay, I'll do that and then have a look and take yourself through it step by step. On there, traversals, yeah, go through your traversals, people. Yeah, remember, in order, pre-order, post-order, or pre-post in order, whichever way around you want to do it. Pre-order, node, left, right. Post-order, node. Oh, sorry, my screen's just gone off. Oh, wait, what's going on here? There we go. Yeah, so pre-order, node, left, right. In order, left, node, right. Post order, left, right, node. Okay, go through those and have a go. Okay. So other than that, yeah, go through your pre, in, post, all your traversals. Go through all those things, and I would quickly just look at back on here. I'd go through two-dimensional arrays and three-dimensional arrays. Records. Make sure you can define a record. Stacks came up, and the code did. Queues has not come up yet. Trees. Binary search trees and binary trees, pretty much the same thing. Linked lists, I would definitely go through linked lists and how to add and remove from them. I definitely think linked lists will come up tomorrow, as well as hash tables. Hashing functions, remember, data gets put into the hashing algorithm, and then that produces a location of where it's going to be stored in a file, okay? And there's some problems with that. Different methods of overflow, progressive, and flag, putting flags in your overflow. And then, yeah, there's your traversals. So I've given you some examples of traversals in there, okay? So, really, I will send that out to you. I'll highlight the things that I definitely think I would go over. I'll highlight those in red on this screen here, and then I'll send that out to you shortly. But how long have we been going for now? I don't even know. It feels like forever. Okay, so keep revising for tomorrow. 9 o'clock in the exam. I'll see you there. Feel free to send me an email after about what was on the exam, because I don't see it till 24 hours after. I wish you the best of luck, and make sure you don't sort of kill yourself trying to do this. Stay hydrated. Yeah, that's important. Thanks, Shaq. And take a calculator into the exam, because who knows what's going to come up. And yeah, any more questions, give me an email. But thanks for tuning in. Thanks for joining in. All right, I'll see you tomorrow.